Welcome, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm super excited to be here with you for day 5 of our Cisco Certified Network Associate Bootcamp. This is a CCNA 200-301 bootcamp. It is a completely free CCNA 200-301, and this is the part 5 of our session. And what is this training that we're doing? We're training Cisco Networking Essentials. And whether you call this Network Administrator training or Network Engineer training or Networking for Cloud Computing training, networking is the heart of everything. So this is very critical cloud computing technical skills, and this is really some network skills training. And if you're a cloud architect, this is a critical cloud architect skill. And this is cloud architect training or network architect training. And really, we'll talk about so many networking and cloud career tips. So I want this cloud network training to be really great because I want you all to have the best careers. So you could look at the CCNA course for beginners. You could look at this as Cisco certification training. You could look at this as a CCNA course for beginners. But really, what are we talking about? What is a computer network and networking and cloud computing and networking in general? And that's what we're here to talk about. And that's what we're going to be doing on this boot camp. We're going to be doing more and more and more networking. Let you guys know, in case you weren't here for the first week, we have the first 4 days available on our YouTube channel. And there's a playlist that covers our completely free CCNA program. So go back and see the previous days. If you haven't seen them, tell others, tell a friend. I want you to have the best networking training experience you possibly can. So just wanted to go over those things with you. Before we begin, I want to mention a few housekeeping things to let everybody know we have a completely free AWS Certified Solution Architect, Associate, and Professional ebook. The link is in the description below. Make sure you get your copy. It's completely free. I also wanted to let you know that this week on Thursday, we'll be holding a live How to Get Your First Cloud Architect Job webinar. You'll be able to come in, ask any questions about learning how to build your best career. We will tell you what hiring managers desire in a cloud architect. We will tell you the skills that you need to learn to get your first cloud architect job. We will tell you how to be the hiring manager's dream hire. We'll teach you how to skip HR to get your resume in the hands of the hiring manager so you can get that first job. And if it was a network architect that you wanted to be or a network engineer, that's the same thing, and you'll be okay in either case because we're going to follow the same strategy. So, I just want to get those points across to you. That's what we're going to be doing. Networking, Cisco CCNA training, the Cisco Certified Network Associate. But most importantly, the whole goal of this is to get you network hired or cloud hired. So let's kick it off with a hashtag CCNA. I'd like to see everybody type hashtag CCNA. When I see that, I know you're here. Deanne, we're super happy to help out. Ash, hello from Seattle. LM, it's fantastic to see you. Eric Stoltz, wonderful to see you. Marty Reamer, cloud hired exactly from Phoenix, Arizona. I'm loving it. Sadie, welcome. Hello. Sarah Ahmed, hello. So good to have you back and love the butterfly. And Marcy, so good to see you back. And Marcy, CCNA as well. Sadie, CCNA as well. LM from Mozambique, fantastic. And Jeannie, I'm always so happy to see you. Tom Orpheus, coming out there from the Netherlands, good to see you. Fantastic. Twinkle, CCNA, Alex, Kalispera Sauce, LM, CCNA. So this is wonderful. We're all here. We're all excited about Cisco networking, and I love networking, and networking is the heart of everything. The data center, the cloud, the network is everything. So let's have some fun with networking. Today, we're going to be getting involved in some troubleshooting, and we're following the official flow of the Cisco curriculum. Quite frankly, I would normally teach the things that we're going to how to work first before I go into troubleshooting. But like I mentioned, I want you all to be able to follow through that official Cisco curriculum and those official books. So we're going to follow this philosophy. What we're going to talk about now is we're going to talk about making sure that we know how to troubleshoot routing. And those are the kind of things we're going to do, and routing errors. So let's talk about debugging or troubleshooting. What is troubleshooting? Troubleshooting is when things go wrong, and trust me, they will go wrong, finding out what's wrong and how to fix it. And trust me, we will be doing a lot of that in networking. Now, we've got lots of ways to troubleshoot, but we're going to walk through a few things. The first thing we're going to actually do when it comes to troubleshooting is I'm going to show you how we walk through it. We're going to go step by step. So let's go back to our routers over here. And in this routers, let's pull up a couple routers. Enable, Cisco. I'm gonna add a second router over here. Let's go to this router. Enable. Okay, so we've got two routers over here. Now, if we look at the routing table in router 1, you're going to notice there's a lot of routes here. So I added a couple of routing things over the weekend to make it a little more fun for you guys. So when we look at this routing table, we can see the following. We can see on this one router that it's got a connected, meaning it's attached, 1.1.1.1. So that's the loopback over here. How do we know? It says a C, which says it's connected. Now, after this, what else do we have? We've got this B, which means, look in the legend, it says BGP. So it means we learned this 2.2.2. route via BGP. So when we look in this routing table, we'll see a couple things. We see a 20/0. The 20 is the administrative distance, or how believable the route is. Now, with Cisco routers, the lower the number, the more believable. As it turns out, eBGP has got an administrative distance of 20, which is pretty darn believable. Given things like OSPF are, realistically speaking, 110. And you can see how this is a pretty believable route. So if we had two routes competing for the same subnet, we're going to choose the BGP because it's more believable. Now you can see we've got another one, 3.3.3 is subnetted. How did we learn that? DEX. So D means EIGRP, EX means external, meaning it was a route that we injected into EIGRP from something else. So how are we going to look at that? Look over here. There's a legend. D, EIGRP, EX, external EIGRP. So you can see that over there. Now over here, we can see a 4.4.4.4 because it's an EIGRP. We can see that via BGP, we've got this subnet, etc. We can see the subnet. So on this router, in the routing table, I should be able to ping 4.4.4.4. I can. Good. No? Actually, let's do this. Let's go to the third router instead of showing you this one. So let's look in this topology. We've got a router, a router, a router. So let's go to this third router over here. Let's see what we got over here. Called the router pizza, show running config. Let's see what's in here. Okay, let's look at the routing that we've got here. We've got EIGRP running over here. Okay, so we can see this. So if I wanted to go to ping 4.4.4.4, it works. Now let's say we go to this router, show IP int brief. Now if we shut down this loopback, right now I can ping this. And this is going to be something interesting. I want you to carefully watch this. Now, the second, if I type this down, shut down, it's going to shut off that interface. So we'll shut it down. Now we'll try and ping it. We can't reach it. So a couple interesting things. If it's not there, we can't reach it. So let's talk about a few ways that you can troubleshoot this. Let's pretend that 4.4.4 is a server. You get a phone call. Hey, Mike, I can't reach the server. What's your first step? Ping. Send an Internet Control Message Protocol message to the server, and if it's alive, it's going to answer you. Ping. We've got it. Life works. It's good. So that's how we look for things. The first call we get, when we can't find something, what do? We ping it. We want to see if it's there. Now, if it's there, life is easy. We know it's awake. Now, let's pretend this was a server. And we just pinged the server. Let's go back to here. Back to our configurations. We'll turn it back on.
You're not showing your screen.
Control E. Now, very quickly, you'll see once at some point the routing protocols are going to converge, and what you see, you can ping it. So now let's back up because it's routing. But if this was a server, you'd ping it. Now, if I can ping the server, somebody gives you a call, the web server's not working, and I can ping that server. Is the network healthy? Everybody tell me in the chat box. If I can ping the server, even if it's not working, is the network providing transport to the server? Yes. Yes. If I can ping the server's up. So if I can reach the server, is it most likely a network problem or is it most likely another kind of problem? It's most likely another kind of problem. Now let's pretend I couldn't ping the server. Well, look at this network. There's 3 routers here. If I couldn't reach this router, there could be another problem. Maybe the problem could be with this link. Maybe the problem could be with this link. Maybe there could be a routing protocol misconfiguration. But we won't know that because we're going to have to debug that and troubleshoot that a little more. So by doing this, we can figure out what's there. So let's look at what the next step would be. If we couldn't ping this because it was shut down, we'd probably want to figure out where it gets stuck. Where's it lost? How do we do that? Well, if I send a message to something that's here and it's not working, I got to figure out how to get there. So I can do a trace route, and that's going to tell me how to get there. It's going to map the network. Now, this is working. Our network's working. So if I do a trace route, it should show us the full path because there's no firewall somewhere. So let's see what it shows us. Okay, it's telling us it's going. It's a little bit slow, but it's going to map out the network for us. Okay, I know the first router hop. It's going to show us the whole path, you'll see. I know the second router hop. And I'm there. 192.168, 1.6. Guess what? That's sitting on this router's interface. That's over here. Now, that's the path because 4.4.4 is on the same router. So see this protocol that we just used, this trace route? It uses something called the Internet Control Message Protocol. Why do we love the Internet Control Message Protocol so much? It helps us figure out what's going on with our network. Now, you see how I just mapped the network like that? This is great. It enabled Mike, the network administrator for the day, to troubleshoot what's going on. But I just mapped the network. Just like that. I can see it. I know what's going on. So if any of you wanted to go to a command prompt on a Windows, you can type CMD and go to a command prompt. And if any of you are on an Ubuntu system or a Red Hat system or Mac, you can go to the terminal and do a trace route to www.amazon.com. Note, go ahead and do it, all of you, or Cisco.com. I don't care. Go and do a trace route. Actually, you know what? It's a great experience for you to do it. So go do a trace route. And if it's on Windows, it's going to be trace RT. And if it's on a Unix or Linux system, it's going to be trace route. And do trace RT or trace route www.cisco.com. Now you're going to see something interesting. Poof. First, you'll see the first hop. You'll see the second hop. You'll see the third hop. You'll see the fourth hop. You'll see the fifth hop. And then somewhere, you're going to get this star, 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 star. And what does that mean? It means you're not getting any information back. So why might that be when you do an internet-facing traceroute? Because what happens is, do you see the way I just mapped the network? This is not good from a security perspective. It's brilliant from a troubleshooting perspective. But if I know all the IP addresses of all these routers, I can actually SSH or telnet into these routers, which is pretty bad, which means a hacker could do this to map the network. So when you go do a trace route to a public-facing internet site, you're going to see hop, 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 hop. And they're getting asterisk, asterisk, asterisk. Next hop, asterisk, asterisk, asterisk. And that's what's going on is the firewalls are blocking the ICMP echo reply to that message. And by doing so, it doesn't let you map their network. So this ICMP thing is a beautiful, beautiful, beautiful thing, but can also help you get hacked. So it's a matter of knowing what to use, when to use it, and why to use it. Oops, that was not what I meant to do. So that's why we're kind of doing these things. So one of the ways on these routers we can do things is we can do what's called an extended ping. And by using an extended ping, we can check our routing. We can source the address from something different. We can send it of a certain packet size. So let's walk through how we're going to do this. I want to show you the different options of a ping because you might need to do lots of cool stuff in your system. So let's just type ping and then enter. Now we could type a protocol. In the old days, it would be IP, IPX, AppleTalk, etc. Target IP address. So let's say we do the same 4.4.4. Now we can send 100 pings instead of 5. We can change the size to 200 bytes. Time in seconds, let's say 2. Extended commands, yes. Let's see what we can do here. Ingress ping, we're not going to worry about it. Source address, wow. Instead of using one of these addresses, let's say we do it from 1.1.1.1, 1.1.1.1. Type of service, we don't need to change it. We don't need to set the fragment bit in the header. Validate, no. Send a standard data pattern. We're not looking for anything complicated. Sweep a range of sizes, sure, why not? Sweep minimum, blah, blah, blah. Okay, and it worked. So you see, this gives us a much deeper test. We were able to send bigger messages. We changed the source IP address. Saying this is kind of cool stuff. We lost one. We lost another one. That's pretty darn good. We're getting some really good network throughput over here. We're changing all kinds of sizes, and we've got no problem. This is a very healthy network. All right, we don't need to keep going on with this forever. We'll see. Oh. I think I set that one to go a wee bit longer than I necessarily wanted to go with all those pings, but we'll let it go through its ping and we'll go back to the content. But that's what I wanted you to see. We can do multiple kinds of pings so we can really source our information. And you're going to be hitting content delivery networks like Akamai or CloudFront or Cloudflare when you're going to be dealing with any of these environments. Okay, so let's get that thing to come back to where we want it to. And then where did this thing go? Hold on. Bear with me 1 second. Okay, so let's see what we want to, let's see what we should go through next. We'll walk through the traceroute command, walk through the traceroute, some more trace routes. Let me show you a different way to do a traceroute when this router is back up and running. We can also do what's called an extended trace route. After we get to the troubleshooting, we're going to start to get into some really interesting stuff. So let's go back to here. Let's go look through this. Now we've got our router over here. Make sure we're on the router. Get to enable mode. We rebooted the router, so let's see if all the routing protocols are up yet. They're clearly not. Show IP route. We'll see when these things come up. Not yet. Let's make sure we don't have an erased router over here. We should have our routes very soon. Not yet. We'll figure it out. Give it a chance to converge, come up, that kind of thing. Let's see what's going on here. Loop left, loop back, loop back, loop back, loop back. All that stuff's here. We've got network 192.168 and Eigrp. We should be up and running. I don't see why we're not. Didn't mean to do that. Well, then we got to find out why not. So we get to do some troubleshooting, everybody. See, even in real life, when you don't plan on it, you find stuff that just doesn't work. So let's look at the routing table on this guy. That's looking pretty good. We're not getting this 1.1.1.1 thing for some reason. So let's show the run, and then let's go deal with the routing on this and figure out what's broken. So the loopback, everybody, is 1.1.1. The loopback 11 is 1.1.1. And the gigabit Ethernet is 1.1.1.1. So let's see what we've got over here, Eigrp-wise. And let's see what we've also got over here, routing-wise. We've injected the 192.168.1.0 into Eigrp, which is the LAN interfaces. And in Eigrp, we have the network 1.1.1.0. So we should be forming an adjacency. We don't have any. So let's see what's going on router 2. Is router 2 not running any routing protocol? That's router 3. Let's go to router 2. Now, what's the IP address on router 1's LAN port? 192.168.1.1. So what's the IP address on this port? It should be 192.168.1.2. Let's see. It is. So can this ping the far end of the link? 192.168.1.1. Ah, well, the first one will be the ARP. The second one isn't working. Okay, so why? What's going on that we can't ping across that link? Why? What should we look? What do we see? What do we see? What do we see? Let's look at this routing protocol. Does anybody see any reasons why we might be having trouble coming across this link? Anybody see any reasons? If you see the reason why this isn't working, put the reason in the chat box. Why doesn't router 1 have any routes from anybody else? The routing protocol is configured, but it's not picking up routing protocols. Anybody know this? Sarah Ahmed, exactly. Robert Timmons, exactly. Ben Christopher, exactly. The interface is shut down. So, this is basic things. So, there's a point when you got to look at something, and when do you bring in the experts? What we're doing right now is not even level 1 support. This is where we've got the super junior people. Is it plugged in? Is there paper on? That's the level that we're dealing with. We'll get to more complicated things when we start talking about routing. That would be tier 2. And then I will show you guys when it's tier 3 or tier 4 or tier 5 when you got to send it to a networking person. So let's go fix this. Back to this router. Remember the interface that you said was shut down? And you saw that it was shut down with the shutdown command. So good troubleshooting, everybody. So interface gigabit Ethernet 00. Int G0/0. No shutdown. Now watch what happens. We're going to get some messages. They're going to show us the interface went up. Now we saw Eigrp make a neighbor change. We saw BGP make a neighbor change. So if we do a show IP BGP neighbor, we've got a neighbor and it's established. Everything's working. So now let's look at this. Show IP root. Look at that. Now we've got some from BGP. We've got some from external Eigrp, BGP, etc., etc. There is a /24, 192.168.1.0/24. Wow. So this router's got a bunch of /30s over here. It's got this /30. And this is the IP address on this. It also has this /30. Now when we go to this other router, we see this /30 and this /30 and the 192.168. Let's go to the pizza router. It's over here. Let's do a show IP interface brief. Again, it's got another 192.168.1.6/30 subnet. So where is this /24 coming from? Why do we have a /24 in BGP? Well, I'll show you why. I'll show you what we did. Now, margin, this is still external BGP. So let's go to this the next router where I advertise this into BGP, and I'll show you what I did. Okay, it's not on this one. It was on the first router. I thought it was. Look at this thing over here. So BGP. Now in BGP, I tell it who my neighbor is. I told BGP to advertise the 11.11.11/32, and we'll talk more about this later. I told it to advertise or at least put into BGP the LAN interface. Aggregate address 192.168.1.0. So I told this router to send a summary route. So remember before when I had you guys doing subnetting and supernetting, and I said this is how we take a bunch of routes down, and this is how we do this? With BGP, I could literally generate any kind of a summary route I want. So let's say I wanted even a better one, config T. Let's say I wanted to go to router BGP 12345. Let's say I do an aggregate address 192.168.0.0 mask. See if it took it. No. This is BGP. So with BGP, what we did is follows. We're adding another subnet. So let's go to the next router over. Let's see if we learned any new routes. Look at this. Via eBGP, we learned 192.168.1.0. See, that's what's called the summary route. And if I wanted to, with BGP, I could only send the summary route. I could send a specific route on 2 different links, which is how we do traffic engineering. So summary route on 2 different links, or realistically speaking, go back and do the same kind of thing we're talking about. So that's the summary route. And that's why we taught super netting as opposed to subnetting. So now let's go back to this particular environment. Now and the reason we're going here is this is reality. This is what you guys are going to be doing. In today's world, a lot of what you're going to be doing is going to be on the cloud, and that's okay. So let's now let's think about this. Now let's go back to this particular situation. And now let's look about a traditional, normal multi-cloud environment. You got your data center over here. You see? You got a cloud like AWS over here. You got a cloud like Azure over here. You got a connection, a private line, and a backup private line. AWS likes to call them direct connections for some reason. You've got a private line and a backup private line to Azure. And the Azure marketing department decided to make up the crazy name Express Connect for this. And then you've got some VPN backup. So you've got this, and this is your environment. But see, here's the goal. The goal is to have this send a single route, 10.0.0.0/16. And over here, maybe you do this. Maybe you have this, 10.1.0.0/16. And then over here, you've got a 10.2.0.0/16. See, by doing this, that's what the whole point of that aggregate address is. You can send one route. And that way, or one route, you can send a specific route on this link, a specific one, and a backup. That's the whole point of what we're doing. All of this, and that's why we're doing it, is to traffic engineer our traffic. So, how do you reach these routers? Let's just make sure. So show run line. Let's go back to our server over here, and let's look at this configuration over here so we can see what we've configured in it. Let's look at the virtual terminal configurations on this. That's very important. Okay, so let's go to the pizza router. Let's look at the running config on this one. Okay, so watch this, everybody. On this router, if we do a show IP interface brief, shows us this. So we know on this router, we've got an IP address of 1.1.1.1. Now let's look at the routing. Let's look at the routing table on the pizza router. Show IP route. Now, if we do this, do we have a route for 1.1.1? We sure should. Let's verify it with a ping. Okay, now if I type 1.1.1.1 in here, does anybody know what's going to happen? It's going to transport me. And wow, look at that. I'm on router 1. If I leave this, look, I'm back to my router. If I do this, it's going to telnet or SSH based upon my settings, and it took me to the new router. I am on router 1. Now I can go look at that running. Now let's look at the routing table in router 1. It's going to be different than the routing table on this because I'm in router 1. Exit. So if I were to do a trace route, 1.1.1.1 on this bottom link over here, it's going to map me the path. There's a reason I want you to see the path. So I can see my first hop from here is the 192.168.1.5. Let's see where the next, which takes us to here. which takes me to dot 1, which is sitting over here. So that's the path. So let's say, for example, over here is where we needed to get to. So if we knew an IP address on router 2, show IP interface brief. Perfect. Let me show the running config to make sure I enabled the virtual terminals on this. Okay, perfect. I did. So what I would ultimately do over here is, if, for example, I did a trace route, and I saw in my trace route from here, my data got lost in this router, what would I do? I'd hop on that router. How would I do it? I'd pick an IP address from that router, 2.2.2.2. Oops. 2.2.2.2. That would open router 2. I'd go to router 2. I didn't set an enable password, so I can't do much. So let's set an enable password for router 2. Now let's go to this router 2. Wow, it took me there. We'll type enable. We'll type the password. And now I can configure this router as if I was local to it. So that's how we've been debugging routers. What do? We ping it. If we can't ping it, we trace route to it. So let's do a little more debugging and troubleshooting while we're here. I'm going to walk you through the way I would troubleshoot a server. It's not working, as opposed to necessarily just the Cisco view. So what we'll do is I'm gonna walk you through a little bit of troubleshooting live. It'll be fun. We'll do it real time and live. You never know what happens live. So let's say over here we've got a network. It's going to look like this. Gonna have a router. Now we got to make routers look like smiley faces, because routers are nice, happy, sweet things. Okay, so we've got all our routers. We'll call it R1, R1, R2, R3, and attached to this, we're going to have a switch, SW, and here we're going to have a web server. So the server is going to be plugged into the switch. It's going to be in a VLAN. The switch is either a layer 3 switch, or most likely it's a layer 2 switch, and we're now routing to this router. While we're at it, let's draw a link between these routers because it's fun. Let's draw a link between these routers because it's fun. Now you're here. You're the troubleshooting person. And somebody says to you, oops, that's not supposed to happen. Bear with me. Okay, so here you are. You've drawn this beautiful environment out. You get a phone call. Hey, Mike, can't reach the server. First thing I do, I ping the server. And it responds, problem solved. Next thing I do, I ping the server. No response. Now what? No response. My next step personally is going to be to ping the default gateway, which is typically the spot right over here. Why am I going to do this? Because if I can't ping the server, but I can reach the default gateway of that server, it means that either the server's dead or I've got a problem with the switch. I don't know yet, but if I can ping the default gateway, but I can't ping the server or the switch, something's wrong. So what do? I go to this router, and from this router, can I ping that server? And if not, I go to the switch and I look at the server. And if it's got a VLAN mismatch, for example, I can see it. If I can look at these two devices and see if there's an access list blocking something, I can look. But if I can ping this gateway and not the server, there's a problem with either the switch or the server, and that is obvious. But if I can't ping the gateway, I probably have a routing problem. So then I do a trace route. Trace route, www.mycatcindy.com. And mycatcindy.com stops at router 2. So I go to router 2, I check the routing tables, I start looking around, and that looks good. So I hop from router 2 to router 3. Look the routing tables back in that direction. I look the routing tables in the forward direction, and I find it. So that's what we're going to do. The first thing we're going to do is we're going to ping it. Then we're going to ping the default gateway. Now, when we ping these things, which do you guys think is a better address to use? So are we going to go do this? And let's say Ivadoikia's got a blue wrench. So am I going to ping the DNS name Ivadoikia? Or if I know that Ivadoikia is 1.2.3.4, her IP address, am I going to ping 1.2.3.4? Well, I'm going to tell you, right thing I'm going to do, I'm going to ping Ivadoikia's name with the DNS name, which is going to say Ivadoikia. And if that doesn't work, before I do anything else, I'm going to ping her address that I know to be 1.2.3.4. Why? If I can reach Ivadoikia via IP address, but I can't reach her by her DNS name, that tells me that there's a DNS problem, meaning whatever maps mycatcindy.com to an IP address, that's going to be the problem. So kind of keep those in the back of your mind. So ping the server. If you can reach it, we networking people are like, hey, life's good. Now, that doesn't mean it's all done, but at least that's the beginning of the troubleshooting. If we can't ping the server, can we ping the default gateway? Can we ping it by the IP address and not the name, which means it's a DNS problem? Otherwise, we're going to have to go router by router by router. We're going to be looking for an access list that's blocking traffic from one subnet to another. We're going to be looking at a missing route. You have a route to the location, but they don't have a route back to you. These are going to be the kinds of things that we're going to be dealing with and debugging and troubleshooting in these environments. But, we didn't go into a lot of detail on routing yet. And because we haven't done a lot of detail on routing yet, this is where we're going to try and get ourselves into some more challenging situations. So where are we going from here? We're going to go to OSPF, which is one of my favorite routing protocols and favorite topics in the entire world. But before we do, and we get into some heavy stuff, there's probably some questions coming from this last section. So what we're going to do is Chris is going to bring me these questions. We're going to answer them, and then we're going to get into some OSPF. And if you guys want, and we have time, I might be convinced to do a BGP webinar or a workshop or something like that too. So Chris, if you want to look through the questions that are out there. Angelo, what is the value of troubleshooting with a team of subject matter experts? A whole lot. At one point, do you call them as soon as you get stuck? Well, I would call them if I was stuck as soon as possible, Angelo. Now, granted, you may or may not have access to being able to call somebody based upon the service level agreement. But what I would do, first thing I could do would be I'd be calling for help. Now, the reality is there's always somebody to call. So, Angelo, what I like to tell people is to be good at your strength. Know your world. And then your network is your net worth. Become an expert at your thing, but find somebody in your company that can help, that's an expert in the other things. Build yourself a team. So where am I an expert? I'm an expert at debugging BGP and PIN messages. That's my world. When BGP is not working, lots of people come to me because I've designed it and it's my world. I'll do the same for OSPF, and quite frankly, I'll do the same for PIM sparse mode and multi-protocol BGP for multicast. Once it gets into switching, I'm calling my switching buddy. Let's face it, that's what I do. So there's always a value in troubleshooting with a subject matter expert. They will identify and find things that you won't. Not just that, you'll learn in the process. So always, always, always a great thing. What an incredibly good question there, Angelo. So Chris, if you want to bring in the next one. Marjan, how can you check an access control list from the router? Well, first, there's going to be a point in this course, Marjan, where we're going to configure some access control lists, and then I'll show you how you can look for them. But it's a great question. So we can configure an access control list on a router, and we will be doing it. It'll be fun. And it's going to be in the router where you're going to see it. Great question there, Marjan. Chris, you can get to the next one. Absolutely. Everywhere in the entire networking world for the most part, /30 for WAN and /24 for LANs. Excellent margin. Chris, you can get to the next one.
Waiting on some to come in.
Wow. And we're getting through without a lot of... so NetStat is different. NetStat, and depending upon the kind of computer you're actually on, NetStat will either showing you open ports, and it's dependent. So if you do NetStat minus RN, that shows you the routing table that's sitting on your computer. Ping is an ICMP echo that says, hey, are you there? And it replies to it. So ICMP, or Internet Control Messaging Protocol, is part of the TCP/IP protocol stack to find stuff. NetStat is basically giving you the status of what's going on your Unix, Linux, or Windows machine. Traceout versus ping. Ping is me sending a message to Chris Johnson on the other end. Chris, are you there? Yes, Mike, I'm here. Traceroute is, I want to go find Chris. So I send the traceroute, and I see that I leave my house, and then I go to FPL, and then FPL takes me to AT&T, and then AT&T takes me to Verizon, and Verizon takes me to Chris's house. That's what you get out of a trace route, Eric. Excellent question. Jacuzzi, can I expand the extended ping in a trace route? Absolutely. Standard ping. Jacuzzi, are you there? So extended ping. I can, instead of, if let's say I'm a router, and Jacuzzi, you're attached to my right arm, which looks like the left-hand side of the screen. So by doing this, let's say that's you, Jacuzzi. Normally speaking, the router would source the interface from the exiting interface of the router into you. But what if I wanted my nose, which is a loopback address, to be the source of the ping? So an extended ping or an extended trace route give you the following abilities: to change the source address of the ping, to change the data size. Instead of like a 64-bit byte payload, you might do a 1500 byte payload. It may, with an extended ping, you can change the pattern of the data. You can change the source of the data. Instead of a standard ping is basically 5 ICMP echoes. An extended ping, we can send 5,000. So basically speaking, an extended ping is a ping that gives us the ability to basically tune it or customize it. Same thing for the trace route, and it's an excellent question there, Jacuzzi. An excellent, excellent, excellent one. Any other questions? So before we go back, I want to know you're not sleeping. If you can do the following: if you're having a good time, if you can like, comment, subscribe to the video, and then let us know that you're here by typing hashtag CCNA, and then we'll get back to the content. There should be a good 60 of you here. I should see a good 60 CCNAs, and then I know to get back to things because I know you guys are here.
While we're waiting on all that, we just had a question come in. I'll pop on the screen.
How does TTL affect ping? Great question. So when the ICMP message has a TTL, if it goes through enough, each router degrades the TTL just like everything else. So if you had a TTL of 5 and you're 6 routers away, you're not going to be able to ping it. Danica, Alexandra, Nyworld Gaming, Twinkle. Yeah, CCNA. Reginald, fantastic. Gabe, it's good to see you here. Sharon, Asaya, fantastic. Sarah Ahmed, Calibus, love that. Jacuzzi, fantastic. Sadie, CCNA. Tosin, CCNA. Leo Parati, CCNA, loving that from Brazil. Eric, CCNA. Abigail Marks, yes, CCNA for life. Networking should be with us forever. Angelo, interesting, thank you. Emmanuel, CCNA, fantastic. Williams, CCNA, wonderful. Eva Doikia, CCNA. Devin, can I explain UTP On the first day, we talked about the pin outs on these cables. So Devin, if you want to go back to the first one, you can definitely look at the pins. Like I told everybody on the first day, I'm a network architect. I'm not an admin person, and I've never made an Ethernet cable in 25 years of networking. Okay, so let's start talking about some OSPF. Now, and we've played with it a little bit along the way because I don't want to drag it out because OSPF is one of my favorite things. But let's talk about it. Routing protocols. They basically build you a map of the network so you know how to reach your destination. And when we talk about routing protocols, we're going to talk about two kinds. Distance vector routing protocols, which are terrible, and link state routing protocols. And what is a distance vector routing protocol? A distance vector protocol is Eva Doikja says, I have the route to this. And I say, thank you, Eva Doikja. And I say, Ash, here's the route. And Ash says, hey, Eric Stout, this is the route I know because Eva Doikja told Mike. And then he told me, and I'm telling you, Eric. And Eric says, Jafar, here's the routes, which I learned from Eva Doikja, from this person, from this person, from this person. So if you really think about this, if you've ever played the game Whisper Down the Lane and you say, I have a green bathing suit, and what somebody else hears on the other side is that you're a leprechaun, and it goes that kind of goofy. So, keep those things inside of your mind. Look at these things. So that's exactly what's going on. So that's what a distance vector protocol does. It routes via rumor. I tell you, who tells someone else, who tells someone else, who tells someone else. Well, if you've ever played Whisper Down the Lane, how accurate was that? Not so much. So distance vector routing protocols such as RIP, something called Cisco made called Eigrp, and then another routing protocol that Cisco made called Enhanced Interior Gateway Routing Protocol, which they like to call a hybrid, what was predominantly a distance vector routing protocol. Those are the ones that route via rumor. Now, alternatively, we've got two link state protocols. We've got the one which we'll cover in this course, which is called Open Shortest Path First, or OSPF as it's named. And there's another one called Intermediate Systems to Intermediate Systems. They're very similar in functionality. Intermediate Systems to Intermediate Systems is a 30-year-old routing protocol, and it's typically used by some big internet service providers. And we love that. And realistically speaking, most systems, especially enterprises, are run using OSPF, or Open Shortest Path First. And it really doesn't matter if you're on Cisco, if you're on Juniper, or any other devices. They run these same routing protocols identical. So when you're on Cisco or Juniper or Palo Alto, or it doesn't matter if you're using network standards. So same way on the cloud, I say don't use this or this. If we avoid concepts like Eigrp, even though it's a good routing protocol, we can intermingle our networking devices with everything. So we're going to be talking about dynamic routing, and the whole point is to build a map of the network. So going back to the static route environment, I've got a link to Chris's house. Why, it's good. And I know how to get to Chris's house. And if that path is good, life is good. But if it's not, we got a problem. So maybe I'll walk you through one more time of the static. No, we did it before. So just kind of keep that in the back of your mind. That's what's going on, is we need to build a map that is self-healing. And because of this, we're using a dynamic routing protocol. And we're going to talk about the way these kind of things work. So let's look at an example. I want you to see what organizations look like. This is current routing. Now, organizations themselves are going to be running their own routing protocols internally. And this is what an interior gateway protocol is. So if you can look in this environment, we've got one organization that's running Eigrp. We've got another company that's running OSPF. We have another company running Eigrp internally. We have another company running Eigrp internally. And another company is running something called OSPF, which is what we're going to be talking to. Now, why does this work? Because organizations internally run an interior gateway protocol that's responsible for their routing. And they connect to external organizations through BGP. So inside of our organizations, we use an interior gateway protocol, Eigrp, RIP, OSPF, intermediate systems. but we connect external entities to via BGP. So when we've got our connections to the cloud, we don't run OSPF to them. Why? Because the cloud is an external entity. So we run BGP. If we connect to two internet service providers, I'm going to load share, we run BGP across both links for the same reasons. For the same reason. That's how, what, where, and why we're doing it. So keep that in the back of your mind. Now, when we're dealing with these algorithms I mentioned, we've got a distant vector, which is routing via rumor. We've got the link state. And how do link state routing protocols work? Link state routing protocols work via the following concepts. They send information about their links, and then the routers run a calculation. So let's talk about this. Let's kind of imagine. Let's imagine we had roads, and the roads all sent some special messages to like some fancy Google application that says, I'm here and up and running. 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 And then when you get in your car and you say, I want to go to Chris's house, you pop Chris's address into your GPS, and all the routes are telling the GPS, I'm here, I'm here. Then all of a sudden, a route gets blocked because there's a tractor trailer accident, and the GPS basically removes that route and redirects everybody. And now you're being moved in a new way, and now there's an ice storm directly in front of you. The road tells this beautiful thing in the sky, hey, I got ice on me, I'm not safe to drive. Reroute. That's why we're using routing protocols. And that's how, so how do the link state routing protocols work, like OSPF? Every route that's there says, I'm here, here's my links, here's my links, here's my links, here's my links, here's my links. And if you know all the roads, you run what's called a calculation, what's called the shortest path first calculation on it, and it builds you the map, and you know to get there. So that's how I get to Chris's house. I get in my GPS, and it tells me, make a left, make a right, make a left. And I have to do that. You know why I have to use a GPS? Because it's Florida, and somebody's will be in an accident on the way of my house to Chris's. And if not, I get lost easy. I mean, really easy. You know, a static route to a static route to a static route, that doesn't work for Mike. I get lost. I can get lost in my own house. And it doesn't have to be that big. I can get lost easily. So I need those directions. I need a routing protocol. And guess what? Routers need cool routing protocols to get our stuff there, so they don't get lost like me. Now, what is this? All these things that we're talking about. If I say, road, I'm here, road, I'm here, road, I'm here, I'm here, I'm here, I'm here. It's called an advertisement. Yes, I'm here. Now, what is it called specifically? It's called a link state advertisement. Why? I'm sending you the state of my links. Up and running, up and congested, up and blocked, down, dead. That's the link state algorithm. So what happens is you got thousands of roads saying how to get here, how to get here, how to get here. They do something. Where are you going to store data? We have a website. We want to store transactions. Where do we put it? We put it in the database. Customer buying patterns, we stick it in the database. So where do we think we're going to pop in all these link state advertisements? A database. So now we got all these devices saying, I have all these links. We pop them into a database, and then we run this math calculation, and we determine the best path to the destination. That's all it is. That's exactly all it is in every stretch of the imagination. So let me show you what it's going to look like. In this environment, all these routers are going to be sending the status of the link. I got a link, 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 all my links. And then after everybody sees all these links, they run that calculation. So it's no different than the roads broadcasting to the magical Google thing in the sky. So that's what's going to happen. So we build a database and we run a calculation from the database. So, you know, let's talk about the process. For this to work, I got to know who I'm talking to. Now, I want to talk to Eva Doikja. It's pretty easy. She speaks actually exceptionally good English, even though that's not her primary language. Bulgarian's her primary language. She speaks Italian. She speaks lots of languages. It's pretty cool stuff. But, you know, that's the key is what are we doing? We're sending information and we're running a calculation on it. So, you know, kind of keep that at the back of your mouth. So first thing that's going to work. Let's say I want to, Eva Doikja's got the blue wrench. So I want to form a neighbor adjacency with her. Eva Doikia, are you there? What am I going to do? I'm going to send a multicast hello. Hello. 224.0.0.5. Hello. 224.0.0.5. Hello. 224.0.5. Hello. 220.0.5. And what's Eva Doikia going to say? Got this message, Mike. Hello, Mike. How's you and how is Cindy today? And I'm going to say Cindy's really good. The metric to Cindy is to get to my house, and it's a little further away because Cindy's in her own bedroom. And yes, Cindy has her own bedroom, even though she sleeps on my feet or on my chest or my head every night. But she has her own bedroom to sleep in during the day. And yeah, she's got her own blankets and she's got her own special pillows. And, Cindy's a very pampered cat, but that's the key. So Eva Doikia, are you there? Hey, Mike, I'm here. Eva Doikia, would you like to exchange routing information? Yes, Mike, I'd like to exchange routing information. So I sent Eva Doikia the routes to my subnets, the routes for my storage area network, the routes for my experimental network, the routes to my cloud, the routes to my workstation. And she's over here because I know Eva Doikia. She's great. She's fantastic. She's doing all kinds of cool stuff. And now there's that. And she also knows how to get to Cindy. And I even gave her the key via a route to the special cat food that makes Cindy really happy, the fresh shrimp and the fresh scallop cabinets, so she can even remotely cook it in the fancy IP-enabled oven and give my cat Cindy some shrimp and scallops, which makes my cat Cindy happy. And that's really what's going on. Is I reached out to reform what's called an adjacency. We have to become neighbors and agree to talk to each other first. So how does that happen? We send a hello message. We negotiate whether we want to get along, and then after that's the case, we do that. So what goes into this hello message? Well, tell you what, I'm going to show you. Let's, and then I'll actually tell you, but let's have fun with it. We've got all these things, we can debug them. So let's go to router. Let's do this. Let's remove the Eigrp from these routers.
Make sure to share your screen.
Thank you. It's so helpful to have that eye in the sky. You have no idea. So let's say let's look at the Eigrp configuration on here. Okay, so we've got config T, no Eigrp, no router. Eigrp 1. Let's do router Ospf instead 1, because I want you to watch what happens. Let's do the network 1.1.1.1 mask 0.0.0. Let's put it in area 0 so you can see it, and then we'll walk through these other areas. And let's do the 192. Let's do this network 192.168.1.0.0.0.255 area 0. Let's go to this other router 2 while we're at it. Let's get rid of its Eigrp configuration. We'll swap it out with Ospf. Okay, so we're going to be on router. I'm going to go to router run right now, and we're going to debug. I want you to actually see the OSPF messages are going to be. So we're going to be debug IP Okay, now on this router, you can see it sent a hello. Now, is it going to receive a hello yet? No, because I haven't fully enabled OSPF on the far link. So you can see right now on this link, hello, are you there? This is reaching out to Eva Doikia. Hello, are you there? Note, it's being sent to the multicast address 224.0.0.5. Now we're just going to see hello. We're going to get no responses. Now on the second router, router 2, once I put this interface in OSPF, we should expect something different. Oh, look at this. All of a sudden, we received a hello from somebody else from 2.2. We're sending some LSAs back and forth. Now we've got a database. Our things are full. So we'll be able to do this. Now, if we go to this config to router and we do a show IP route, we're going to see some routes via OSPF. Can we ping that 1.1.1? We should be able to. We learned it via OSPF. Let's go to this router. No debug. See, as you can see what happened. Now, if we go to this router, show IP OSPF, we can see the link states, the database. It's got a database. And what do we see? We can see the link for 2.2. We can see where it came from. We can see how many seconds it is. We can see where our things are coming from. So we're going to talk about a couple of different kind of link states. They don't cover it in the CCNA program, but I might do it anyway. So what you're going to see is you're going to have a couple of kind of link states. You're going to have something called network links, and you're going to have links and then router links and then network links. So yeah, this is the first type of links which you get per link. This is called the router LSA. This is a network link which is generated by the designated routers, and then we're going to have a link which goes in between areas, goes intra-area links, and I'll show you what I mean by that. So now let's do this. On this router, let's add another loopback. And before we get to that, let's just see let's make sure everybody understands it. So what did we do here? We streamed hello, hello. As soon as we agreed hello, then we decided to be neighbors. Eva Doikia and I, we basically shook hands. Then Eva Doikia sent some scallops for Cindy, and I sent Eva Doikia a beautiful t-shirt that had Cindy's photo on it saying, thank you so much for feeding me. And it was personally signed by my cat with her, really horrible handwriting, but it was cute anyway. So, that's kind of what's going on. We're building a database. So if you notice, the advertising router, what it used is the highest loopback address to be the, to be the router identifier. So kind of keep that in the back of your mind that routers use a 32-bit identifier. And it's based upon the OSPF router ID that you tell it or the loopback address that you pop on it. So hello, are you there, et cetera, et cetera. So let's walk through the neighbor state. And we've got two routers like, hello, do you see me? Yes, I see you. And then after that occurs, what the routers do is they start exchanging LSAs. I've got this link, I 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 got this link. And then they're basically exchanging their databases. They share each other's links. And then after they do that, they run a shortest path first calculation. Done, done, and done. So let's talk about a couple of timers. The hello interview. How often you send hellos? Dead interval. How many hellos do you need to miss until you mark the link as dead? Pretty much it. So, a lot of times we make complicated areas mean, and then let's talk. So let's talk about this. So now let's talk a little bit about the architecture of OSPF. So I'm going to walk you through this. And realistically speaking, we do it in the following methods. Actually, before we do it, we may have a fair number of questions on this content. So maybe I should answer some questions And then after the questions, I'm going to walk you through the database. So let's do that. Looks like we had a bunch of questions from what I can hear. Eric, I have no idea. Some are the highest loopback, some are the lowest loopback, et cetera, et cetera. Each protocol's got its own standard. Like lowest is what you use for a spanning tree, for example. LM, what does area 0 mean? That was what I was going to get to next. How does the router choose between an OSPF route and an EIGRP route? Wow, that is an exceptionally good question. So when you look at all these routes in the routing table, they have something called an administrative distance. So whatever the lowest the administrative distance is the answer. So when I showed you BGP had an administrative distance of 20, and I showed you that OSPF had an administrative distance of 110. If you learn the same route from BGP and the same route via OSPF, then you will choose the BGP route. EIGRP has an administrative distance of 90. Excuse me, OSPF's administrative distance is 110, which means that if you learn the identical route from OSPF and EIGRP, you will choose the ERP route because it's got a lower administrative distance. OSPF's is 110 and EIGRP's 90. So that's realistically speaking how this is working. Now, if you wanted to make OSPF more believable than EIGRP, you just reduce the distance of OSPF through the distance command, or you increase the distance of EIGRP to make it look less believable. But that's all based upon the administrative distance, and we'll be playing with that. I'll let you play with that on the lab. That's a good point. It's not typically something you do until the CCNP or maybe even CCIE, but we can play with it in one of the labs. Good point, Angelo. I'm happy to do that. Chris, you can bring in the next one.
That was it. I just wanted to make sure we took care of this before we got too far down any rabbit hole. in case we couldn't come back to it.
Okay, that's a great idea, Chris. We're going to go down some fun rabbit holes. So while we're at it, if everybody's here, type hashtag CCNA. Excellent. I see you guys are here by typing CCNA. I like knowing you're awake, you're alert, and oriented. You know, we take pride in our Cisco Certified Network Associate courses, our CCNA courses, the way they call it, or for the CC exam 200-301. We just want everybody to be successful. Okay, so now let's talk about what goes on. So with OSPF, you got to look at it this way. What's really going on is we're trying to segment our network. So everything we do is about scalability, 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 and more scalability. So the way OSPF works is we create something called a backbone. Now the backbone, these are our most critical routers, the most critical routers that we have. The backbone, these routers need to be the smartest, biggest, and fastest routers. So by doing this, these routers need to know everything. They're like the Oracle. They know everything. Everything. Like that song, Everything's Going to Be All Right. So these routers need to know everything. And this is also, it's called Area 0. So LSPF specifies the ability to basically segment or modularize or decouple your network. So this is called Area 1. Let's say we make it Area 1. And there's some sci-fi thing they talk about Area 51. So while we're at it, let's make an Area 51. It doesn't matter. We can name our areas anything we want. We can make this an Area 2. And we can make this an Area 4, just because we chose to. Now what happens is each of these areas is connected to the backbone via a cable. or multiple cables. So in this protocol, which creates a link state database, which stores the links in the router, it's not like we're going to be using MySQL or Postgres or MongoDB or things like that. This is just part of the routing protocol, and it's going to sit on the routers. So what happens is we're going to have 5 kinds of link state advertisements. There's more than, but we're going to talk about the 5. The first one is the ones that are generated by the routers. Hey, I'm here. The next one is generated by the links. The next kind of links, the advertisements are going to be links that we get from external areas. And the next kind of links are going to be things that are related to external entities. And we'll pop this. I'll show you what I mean by external. Let's just call this Eigrp. So in an area, you have access to everybody's information. What does that mean? Every router, every link in my area, I know about everything. And anytime anything changes on any link in the center, I run a full recalculation. So what you could imagine is if we had 1,000 routers in this backbone and we all shoved them all together, all these routers are going to be screaming, I got links going away, I got new links going away, new links. Imagine a database that's got 50,000 links in it, that's going and coming. It's going to be recalculating. CPUs and the routers are going to go high, router's going to crash, and it's going to reboot, and your network is dead. So what do we do with web apps? We decouple them. Web tier, app tier, database tier. What do we do with networks? Core distribution access layers. What do we do with our routing protocols? We segment them and decouple them. So with OSPF, we have 5 kinds of LSAs. We have type 1 and type 2 LSAs. They are all the links inside of an area. Inside of it, the area 1, what are we going to have? We're going to have a minimum of a type 1 LSA. We're going to have a type 2 LSA too. Minimum we have to have there. Now, this backbone needs to have its type 1 LSAs, needs to have its type 2 LSAs. One is based by the router, one's created by the link. Now, area 1 is not part of area 0. So area 1 is going to send a summary of its links. Now that's going to be called the type 3 LSA. I didn't make this up. I didn't make up these goofy names. But if you really think about it, every area must have its type 1 and type 2. Type 3, and the backbone has to know about this stuff. Now, let's say you wanted to tell OSPF about some routes you learned via another routing protocol, like Eigrp or BGP. I don't care. Although you wouldn't redistribute the entire internet routing table, but it doesn't matter. Heck, it could be a static route you wanted to redistribute. Meaning redistribute, meaning, so Iva Dojke speaks Bulgarian. I speak Greek. Redistribution is translating Greek to Bulgarian. That's all it is. Taking the information from Bulgarian and turning it into Greek, and vice versa. So that's what we've got here. So now, when this stuff gets here, this is now called an external link. And an external link is a type 5. So anything that we learned externally is what's called the type 5 LSA, which means which is an external LSA. It would be helpful if I could type. And this is called the type 5. So the next type of LSA describes, and I'm going to describes which router can reach these external routes. So what's called a type 4 route is something related to ASBR reachability, and I will go over that right now. So here's what we've got. This is called the backbone. Any router that borders between the backbone and another area. So let's say we've got a router over here that connects us to this other area. And it's That is called an ABR, or a boundary router, an area boundary router. Because why? It's connecting OSPF to an external area. Now, this particular router, because it's bringing in something else, is called an ASBR. And realistically talking, it's bringing in external LSAs. So what we have in OSPF, we're going to have realistically 5 kinds of LS. Well, 5, well, more, but I want to keep it relatively simple. We have the type 1, which are generated by the router, and the type 1 and 2 are generated by the router and network. They exist in all areas. Now, when area 0 will know all of its own type 1s and type 2s, but each additional area will only send a summary of its LSAs. So kind of in the distance vector, hey, Eva Doikia, I've got routes to this, and she says, okay. And then Eva Doikia tells her friend Abigail, and then Abigail goes and tells her friend, I'm drawing a blank right now. But anyway, you guys get the concept. So distance vector, route by rumor. So OSPF, intra-area, shortest path first algorithm. Intra-area, they use like a distance vector. Hey, I've got the routes for this. I've got the links for this. And then externally, you got that ASBR. So, I know I went into way, way, way more depth there. Now, the next thing we have to understand is on regular links, we just have OSPF routers. But when we're dealing with something called broadcast multi-access networks, it's a little different. So if we had 2 routers and a serial link between them, but a WAN link, what do we have? We have a single wire. Life's really good, like my iPhone, just a cable. Everything is perfect. But now with Ethernet, we could potentially put 30 routers or 200 routers on the same subnet. We could. And if we put all these routers in the same subnet, we're going to have an election. And we're going to have one primary router. So we have a war. One router wins. And then we have a backup. Now what happens is you've got the designated router that basically sends the information. Okay, I got you. You're over here. This is the information. And it tells all the other routers on the subnet. And you've got a backup designated router. Why? Because 1 is none and 2 is 1. So you can't just have a designated router. You've got a backup one. So you've got a primary designated router. Hey, these are the routes. These are the routes. These are the routes. And you've got a backup designated router saying, hey, by the way, these are my links. These are my links. Now you know what we're talking about and why we have them. So we're going to have the concept of a backup designated router and a designated router. So if we go back to our things and we're running OSPF, do you think maybe we can see some of this stuff? Let's go see. Let's go find out. Let's go back to our server. Let's go back into here and let's walk through some of this OSPF stuff we can see. Enables Cisco show IP route. Let's make sure you can see them. We got some routes via OSPF. So show IP OSPF database. You can see that we only have a single area, so we don't have anything. I'm going to generate some other, I'll generate some external routes for you so you can see the LSAs in a minute. But I just wanted you to just see this, especially there. I just wanted you to get a feel for it. So you can see this. So now if we do the show IP OSPF neighbor, we can see a little bit about the neighbor. Now look, the neighbor is full and it says BDR, backup designated router, which means it's number 2 in the election. Well, there's only 2 routers, which really means it lost the election. So now if we do a show IP OSPF neighbor, the other one should be the designated router. And you can see full BR. Okay, so now let's do this. While we're at it, let's do a show running config. Let's see what we got in here. Okay, so let's do this. Config big T interface. Let's create a new loopback 1. Let's do IP address 13.13.13.13. No shutdown. Now let's go to our OSPF configuration. And let's put this subnet in there. Let's do the 13.0.0.0. Oops, the 13.13.13.13. 0.0.0.0. Now, instead of putting it in area 0, let's put it in area 1. I just created a new area. Now, let's go back to this router, and let's see what we see. If we go back to the database, now look what we see. We see the router links, we see the network links, and now we see the summary link. You see that? Heck, while we're at it, let's add some external links to it too. Let's go to config T. Let's do interface, loopback 2. We don't have a loopback 2, right? Let's do network. Let's do IP address, IP, ADDR. Let's do 14.14.14.14, 255.255.255.255. You probably don't need to shut it down, but it's just my practice to do it. Now let's do this. Now router OSPF 1. Redistribute. Connected. Metric. So say subnets. Metric. 1. Now let's go back and look at our database over here. Now notice the database changed. You can see lots of things that are different in this database. Look very carefully first. The first thing you now see is you see the type 1 LSAs that you had before, the router LSAs, then you see the network LSAs, then you see the type 3 LSAs, and then you get this type 5 external LSA. What is that? It means it's not coming from OSPF, it's coming externally. We're learning it externally. And let's look at the routing table and see if it looks the same way. Show IP route. Now, when we look at the routing table, we're going to notice a couple of things. Let's look to determine the administrative distance over protocols. So this is learned via BGP 2.2. The administrative distance is 20. This is connected, so it's got no administrative distance because it's on the router. We know it's accurate. Now, this 13.13.13, it says an O, which means OSPF. But it doesn't look like this O over here, which we learned via OSPF. Instead, this O says OIA. What does that mean? It means it came from another area. We're area 0. It came from area 1. OIA. And now there's this subnet that I redistributed in. And it says OE2. So we go to our legend. O, OSPF. OIA, intra-area. E1, external LSA type 1. E2, external LSA type 2. Poof. Guess what? We're running external LSA type 2. And that's what we can see in the routing table. So this OSPF protocol is kind of cool, huh? It's fast. It works real well. It's really good. So on the LAN, like I mentioned, we've got an election, designated router, backup designated router. It's kind of like me and Chris. If I go down when I'm going on vacation next week, Chris is going to be there. He's going to make sure everybody is successful. I'm the designated router. He's the backup designated router. When Chris is gone, when Chris is covering for me next week, Leopoldo will be Chris's backup designated router. Whatever the case is, this exists in all parts of the world. We don't need to make routing protocols that complicated. We have an election. We've got a backup winner to the election. And then if we need to, we have a new election and everybody else gets there. So I kind of love this stuff. I think it's kind of cool. So what goes on is it's going to be like this. We have this election pattern. This person becomes the designated router. They all communicate back and forth to the designated router, and that's what makes everything work. That's why we do these things in networking. That's why we do it. So let's play with it a little bit. Let's think about the things. When you just form a neighbor relationship, hello, Eva Doikia. And she says, hello, Mike. We are in a two-way state. Just two-way. We're halfway there, halfway there, halfway there. Then all of a sudden, Eva Doikia gets all the LSAs that my cat Cindy sent her. she's got a picture of Cindy doing this, a picture of Cindy cleaning our fur, a picture of Cindy jumping up the stairs of my house, a picture of Cindy chasing aluminum foil balls, a picture of Cindy on her back, a picture of Cindy doing everything. Then what does it say? It says full. So, for example, and I drew a slide here. So we initially come up, Ivadoik and I, and we're two-way. Cindy, the cat on my end, sends her all her links. She sends all of her links about all that cool stuff that's going on in Hungary. I know how to reach all of her cool stuff in Hungary. She knows how to have a private conversation with Cindy the cat, can access my files, and everybody's happy. That's what we're talking about with these shortest paths for Earth. So now, how does it work? How do you do it? So we do it as follows. Everybody sends a list of costs to their link. So if we know this link costs 10, and we know this link costs 30, and this link costs 60, we can aggregate a cost. So why is OSPF so useful? And why was RIP and all these old distance vector protocols so bad? It was the way they ran the calculation. So think about this. This is like the old distance vector, RIP. And we're going to swap it out. But let's just say we've got a couple of distance vector protocols. So, okay, we've got this via an old school distance vector protocol. This person tells this person about the route. This person tells this person about the route. It's not the most reliable thing in the world, but that's the way the distance vector protocols work. Now, how does distance vector protocols work? How far away is this subnet? Let me put an Ethernet segment over here. How far is this Ethernet segment away in RIP? 1 router hops, 2 router hops. That's the metric. Now let's pretend this is OSPF. Actually, let's do this. Now with RIP, let's add 2 links or a distance vector protocol. Now the top link over here in a distance vector protocol is 100 gigs. The bottom link over here is 1 gig. Not even sure. Well, I don't even know how I got that upside down, but I'm never going to figure out how to straighten it back up. So, so in this particular case, we've got a single 1 gig link. In a distance vector protocol, which direction do you take? Do you take the top link or you take the bottom link? It's random. One packet goes over the top link, one goes over the bottom link. Let's make this even worse. Let's pretend this is a distance vector protocol. We've got these 2 options. This is 100 gig. This is 1 gig. And you've got a choice where you can go straight from this router to the server. Or what you could do is you had the same server and you had a 100 gig link to the server this way. And this is 100 gigs, which is faster from a networking perspective. Assuming, hold on while we're at it, let's just add another one of these. So in this particular environment, what's the best path for this? I want you guys to tell me who has what's the best, most efficient path to this route, to this web server for a high throughput environment. Is it on this is it on this link, which is 1 hop, 2 hops away? Or is it over the top link, which is 1, 2, 3 hops away? Which is the faster way to get there? Which is faster? Tell me in the chat box. The top link. The top link. The bottom link has nothing to do. The bottom link is the worst path because over here we can do 100 gigs all the way there. On the bottom link, we've got 100 gig bottlenecked by 1 gig. So we don't want to use this, but if we're using a distance vector routing protocol, we're going to use the bottom link. which is terrible. Now, if we swap this out with OSPF, we've got OSPF over here. OSPF is going to calculate the cost, and it's going to say this is harder to get to than this, and it's not going to be looking at these things. So that's what we're talking about. We're talking about choosing the optimal path, and we don't get that from distance vector protocols. We get them only from link state protocols, because link state protocols are keeping track of what's going on. They're looking at the connections, etc. So that's why we really don't use distance vector protocols for the most part anymore. So now let's think about how big OSPF can actually get. I really want you to think about why we segment and why it matters so much, and think about how critical this is. Because if we go back to this environment, let's go back to a place where we draw another slide in. If you have 100 of these, and 100 is nothing. I work on networks with 10, 20, 30,000 routers, and that's still nothing. I've worked on a lot bigger than that. So let's say you've got all these things in your network. That didn't work. Let's just say we got a network with all these routers in it, and it's an ugly looking box. Who cares? Every time any link on this entire network dies or moves, with every recalculation whatsoever, there's a new LSA. So literally speaking, if this port was connected to a PC and it was only one PC and you rebooted it, realistically speaking, everybody else is going to need to know that this link went down. That's why we're segmenting these, because these links get so much so fast with every one of these things constantly running a calculation. You got to remember, routers aren't using in general 128 core servers with 6 terabytes of DRAM. Routers have relatively small CPUs for the most part, because they're only designed to route packets. They're running a routing protocol. They're not running graphical user interfaces. They're minimal devices that have ASICs and devices that are designed to forward packets fast. So this is our area 0. Everything that occurs here, we need to know about everything. Everything. So by segmenting it to here, if this is the area 1, the only thing that we need to send over here are the summary routes. Why? Because there's only one way to get to area 1 through this cable. Likewise, while we're at it, if we had a branch office, the branch office might need to know about everybody's routes locally. But does the branch office need to know about the routes in area 1? Maybe. Let's see. Does the branch office need to know about all these routes in the center? Maybe. What if the branch office only has a single link to the data center? Just a single link. Now, if this branch office, let's say the branch office is a Starbucks, and it has one link back, does Starbucks need to know about every one of these links in here? No. Does Starbucks need to know about the information over here? No. Could the Starbucks have its own local subnets and just a default route pointing to this thing? Yes, it could. So does anybody have a networking background? Know what type of area this is called if it only is allowed to have type 1 LSAs and type 2 LSAs and nothing else? If you know what that thing is called, only type 1 and type 2 LSAs, type it in the chat box. And this is going to be some tuning that we would do in an OSPF. We only need to know about our local stuff at the Starbucks and how to get to the cloud. So what is this called? What is this called? What are this called? This is called a totally stubby area. So network brow, good try. We'll give you some OSPF knowledge, but good. This is a totally stubby area, not a stub area. Why? A stub area has type 1, type 2, and type 3 LSAs. But here, all we know is about our router LSAs and our link LSAs, and that's called a totally stubby area. A totally stubby area. So it's totally stubby. Now over here, we've got an area, and in this particular area, we want to redistribute some external subnets. But we don't want, by any stretch of the imagination, we don't want any type 3 LSAs or type in this area. But for some crazy reason, we want to redistribute some RIP routes into this OSPF area. Does anybody know what kind of area this is and what type of LSA we're going to be using for this external one? I'll bring on the Jeopardy music. Do 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 pop 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 boom 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 bump ba-dum bump 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 bump. Okay, anybody that knows networking, what kind of area is this that only allows me to take in an external route and an external area? But wait, anytime we use any kind of stub area, we're not allowed type 5 LSAs. Oh my God, how do we get external LSAs in an area that's not allowed it? Does anybody know what this is called? Okay, this is called a not so stubby area. And when you hear NSSA, this is called a not so stubby area. So the rule of a stub area is you're allowed to have type 1, type 2, and 3 LSAs. The rule of a totally stubby area is you're only allowed type 1 and type 2 LSAs. The rule of a not so stubby area is you can have type 1 and 2 LSAs, and you can have external LSAs that you redistribute. But we got a problem here. The OSPF specification says you can't have a type 5 or external LSA in anything that resembles a stub. So we've created some new wacky LSA called the type 7 LSA. What is a type 7 LSA? Identical in every way to a type 5 LSA, but it's one that enables us to break the rules, meaning in an area that's a stub area where we want to redistribute a stub route, we call it a not so stubby area. I didn't make it up. It's been going on for about 30 years. Anybody with a CCNP, CCNIE, or anybody that's doing any kind of routing or is going to be working with stub areas, not so stubby areas, and totally stubby areas. Why? See, let's say this router has got 800 OSPF routers. This might have a database of 50,000 or 100,000 LSAs, which would mean that the Starbucks router can't handle it. Now, a $100,000 router could, but a $10,000 router we're going to stick at Starbucks cannot. So by creating a totally stubby environment for our branch offices, we can enable optimal communication between subnets in their office. And if they only have one egress point, we can just give them a single route. Now, with the not so stubby, it's the same situation. Maybe we want to send everything through the backbone, except we have one route that we learned from some Linux subnets. And that's why they're not so stubby. No big deal. Now let's create a regular stub area. We've got over here. Now in this area, let's call it the campus. And we've got a couple of links. So we want all of the type 1 and type 2 LSAs, but maybe we only needed a summary to get to other branches. And that's why we would make this a stub area. And by doing this, we can minimize the data that's there. So decoupling. Now, wait a second. Mike drew a cloud. When he drew the cloud, he was trying to do this. He wanted to come up with one subnet over here, 10.0.0.0/16, and then he had a cloud, which is AWS, and he wanted this to be 10.1. And then Mike said, for Azure, Let's make it 10.2. And heck, while we're at it, because, if we want high availability, we're going to use multiple clouds. Let's add Google while we're at it. I love the Google Cloud. It's a fun cloud. GCP, because that's mostly what we network engineers are doing. We're either building the clouds or making the clouds work or connecting the clouds. So now we've got links to everybody, links to the primary, links to the backup cloud, links to the secondary backup cloud. Now, in this particular environment, if we only send one route to AWS, did we overwhelm AWS with the routing capability? Not one bit, no big deal, not at all. Did we overwhelm Azure with by sending them thousands of routes, or did we just send them a single one? No big deal, we sent them a single one. We also sent a single route to Google. Is this any different than this? No. This point of this is the same thing. Now, if we were designing our architecture, and this is how we designed them, in the core of our systems, we've got a bunch of really high performance routers. And this is what it's going to look like, your traditional network. We've got this. I want this to hit home because otherwise it's just, a bunch of type LSA nonsense. But if we've got a link like this and we've got link aggregation groups between these things, links here, links here, links here, links here, links here. Oh, wait, this looks like a nice area 0. That looks like an area 0. And this distribution layer, so you could call this core. Actually, let's do this. So with OSPF, they would call this core. And then they would, in OS, this is core / area 0. Now, the next thing we typically do is something called the distribution layer. But as a distribution layer, it's a way to decouple your things from the core. Now, this distribution layer, realistically speaking, is going to be its own area. And generally speaking, we have these little access switches. And these little access switches, typically speaking, plug into these distribution layer switches. So these feed into these. That's just what we're, I just do the same thing. This feeds into this. This goes from here to here. Now this distribution layer feeds, goes from, say, here to here, and say here to here. So what you can see is we've been decoupling our systems forever. And if this is area 0 and this is area 1, fine, it all works. Or if it's route aggregation to make sure that we don't send too many routes to our cloud providers, same thing. If it's OSPF and we're decoupling by creating areas, it's the same thing. So realistically speaking, it's all the same. Whether it's OSPF, core access distribution, or adding a 3-tier web application where you're separating your web servers, your app servers, and your database servers. The whole concept is to decouple your architectures. Why do we decouple them? Because go back to here. If this one switch dies or makes a lot of traffic, and it goes away and it's got links flapping, we can constrain it over here so the core doesn't see it. So, most companies, they've got the CEO, you can't find their phone number, ever, no matter how hard you want. They've got a secretary in front of them. You try and call the CEO, they don't let you through. It's called the gatekeeper. It's the same thing. They're trying to make their people scale by going out further and further and further apart. That's what we're doing. We're dealing with modularity. We're dealing with scalability. So let's go through these areas one more. And this is, again, way, way, way above the CCNA level. This is going into the CCNP level and to some degree the CCIE level. Why do we like OSPF? Let's go back to it for the following reason. We like them that they can figure out the shortest path first calculation by calculating the bandwidth of the links. We like that they're accurate by building a whole map of the network, and we like that we can scale them with regards to areas. By doing that, we can create some scalability. So type 1 LSAs, router LSAs, type 2 LSAs, network LSAs, type 3 LSAs, LSAs that describe intra-area routes. Type 4 LSAs, how do you reach the router that's closest to the router that's bringing in external routes? Type 5 LSAs, external routes. Type 7 LSAs, the same as a type 5 LSA, but in a not so stubby area because you're not allowed to have a type 5 LSA. So what happens in a not so stubby area, like the one that we drew over here? Over here, we've got some things. We've redistributed the BGP route. It's a type 7 LSA, but it gets converted to a type 5 LSA when it gets sent in. And then OSPF area 0 gets to see a type 5. That's how it works. That's how it works. So all this, core access distribution, OSPF areas, 3-tier web architectures, queuing systems. Same point, same principle. Separate your layers so that what happens in one part of your systems doesn't happen in another part of your systems. Let's open this up. It looked like there were some people, especially I went pretty deep into OSPF fast. Didn't mean to do that. Hold on a second. So, Chris, are there any questions? Because I would assume there might be. And if everybody's got a question, I'd love people to ask them now before we move on to more complicated areas. Anybody have any questions?
Are you looking at StreamYard?
Oh, so that's the problem. I've got a lot of windows open. Is core access distribution a 3-tier architecture? Absolutely. And margin, that's been recommended by Cisco for about 2.5 decades. And I got to tell you, it's the most effective network architecture I've ever seen. I know lots of times people are now doing what's called collapsed core. And what they're doing is basically running monster core routers and then plugging their servers into the one switch away. I don't like it. I'm telling you, I've ripped out a lot of those systems because they don't stop problems when they occur. They're good systems, but I want something to really let my systems totally fall apart and still work. OSPF is designed 100% for routing. Now, OSPF, because it's a link state routing protocol, does have some additional LSAs that can be used for like congestion analysis with regards to MPLS traffic engineering. But OSPF is completely designed 100% just for routing. BGP is only for routing. OSPF is only for routing. Just routing. Good question there, Eric. Angela, yeah, these names, I don't know where they came from. Even Doik, yeah, totally stubby, not so stubby. Yeah, that's kind of a cute topic. Kind of stubby, but not really. Exactly, network bra. It's like you write a specification, and then you got to write a rule to break the specialization. Yeah, area on a stick, Angela. That was funny. I remember doing that router on a stick back in 1997. I remember thinking it was bad then, and let's face it, I like it even less now. Chris, are there any others here?
Not yet.
All right. Well, how many of you guys want to build out a nice, fun OSPF lab where we build it out, we put multiple areas in it, we build a core access distribution? Does that sound fun for everybody? All right, let's do it. So let's bring this a little bit. Let's do. Okay, so let's build a new lab. We're gonna make it fun. We're gonna have to be real. We're gonna have to get kind of fast with this though. So we're gonna say we add 8 nodes. And for this, we're not going to hopefully not need all 8 nodes, but let's do it. So I want you guys to help me configure these things. Let's pretend I don't know how. Oops, bear with me. Okay, so let's have a little bit of fun over here. Oh, wrong one. Let's open this up. Let's give ourselves a couple of routers. Let's say we add 6 of them. Okay, let's pop one over here, one over here, and then let's say we pop one over here, and we're going to make these all connected. Okay, so 1, excellent. 2, excellent. 3, because this way you get to walk through a full, you're going to get to see the full database. This is your traditional area. Okay, so let's go to router 1. Let's give it a base configuration. Hold on. Let's start all these routers up so they'll be ready when we need them. Go to this router. We're going to be a little fast when we configure some of these interfaces because we don't have a lot of time. Bear with us a minute. All right, slowpoke routers, wake up for us, wake up. This should be a really good fun lab for everybody. Because what we're going to do is we're going to install OSPF Area 0. Then we're going to add some external stuff. Okay, so we're going to make this pretty easy. All right, let's get through this thing, and when it's ready, oops, we'll get started. Okay. Router's up. So let's configure this fast. Let's give it a host name and give it a password. So we'll use the host name command. Oh, won't even let me do that. Host name R1 int LOO IP ADDR 1.1.1.1. Configure this one over here, G0/0/0/0. Let's say we do IP address 172.16.0.1 255.255.255.252. No shutdown. Router OSPF1. Let's enter the loopback information. How do we do it? We loop, the loopback was 1.1.1.1, so we're going to do an exact match. Let's pop it in area 0. Then let's also add the WAN link, that 172.16. 1.0.0. Remind you, I've got an extra period in there, so it's going to break things. And then we probably should configure the console ports. Didn't mean to type that. I was going to go. Now it's going to go try and telnet it's going to resolve the DNS name for telnet, but we'll get there in a minute. You can see it's trying to resolve that. Okay, so let's do this. Config T line V GY 04. Okay, so this is router 1. Now, we probably should put on router 1 a link to this subnet as well. So what link is this? Interface G0/0, 0/1, IP address 170. Well, if the last one was 172.16.0.1 and 2, what's this one going to be? Make sure we didn't make any mistakes. We've got 2/30s here. Excellent, excellent, excellent. So, fantastic. Now, can we grab this? Let's go over to here. Now, on router 2. No, we don't want this initial configuration dialog. Configure this. Let's change the host name so we can find it. Host name R2. Let's make sure we can telnet SSH into them. So put an IP address in the loopback. Two 255. Let's make it a host. Okay, so now we're at router 2. So we're at router 2. What's the IP address on this link of G00 on the other side? If you don't know, you can see it over here. It's .1. So what's the IP address? The IP address is 172. Okay, we're going to be on this side, 172.16.0.2, right? What are we going to need on this link? We're going to need another link on this side. Now, on this link, we've never been on the subnet. So which subnets have we used so far? We've used the 0 subnet and the 4 subnet. So where does the next one begin? .8? So let's do this. Interface. And what interface is this going to be over here? G0/1. We can do 172.1 IP address, 172.16.0.8, right? Or dot 8 would be the subnet. So what's the next address? Dot 9, 255.255.255.252. Let's go to OSPF here, router OSPF 1. Would help if I could spell. Over here, we can pop in the loopback 2.2.2.2, 0.0.0.0, which means exact match, area 0. Stick in an exact 0. We could actually, well, we can do a network statement, and we can basically do 172.16.0.0, 0.0.0.0.3, which is the wildcard that gets that subnet, area 0. And then over here, what's the next one we're going to do? We're going to get the dot 8. Now we're going to look at our interfaces and see what's going on. Show IP int brief. Okay. Oh, wait. So this link is down and this link is up. So we probably should turn that link on. Config T interface G 0/1. Let's do a no shutdown on it. Save this. Now, is anything going on yet? Do we have any routes? If we do a show IP route, I didn't see any OSPF neighbor change. Did you? None. Okay, so why? Let's go to this router over here. Let's see what we got. Show IP interface brief. Okay, 172.16.0.0 is one. Can we ping the 172.16.0.0.2? That's not good. Oh. Does anybody see the problem? We got a real problem here. So look at the interfaces on this one. Show IP int brief. Now this is an obvious misconfiguration problem. Note, I attempted to put this address on gigabit Ethernet 00, and instead I put it on the loopback. Config. That's why it didn't work. Config, because you got to be on the same subnet on both sides. Config T. Interface loopback 0. Interface LOO. IP address 2.2.2.2, 255.255.255.252. Now let's go to interface int G0/0. And now let's put the address that we really wanted to put there in the first place. IP address 172.16.0.2, 255.255.255.252. Let's turn that interface on. Let's see if anything happens now. Configured it. Find protocol. Oh, look at that. OSPF neighbor changed. Wait, are we going to have any routes now? Sure are. Can we reach that 1.1 subnet? Sure can. So now I guess we got to go do router 3, huh? And then we'll add some other areas together. So no, we don't want to enter this ridiculous configuration dialog box. We'll give it a minute. And then we're going to add other areas, redistribute some stuff. We're going to have a party time with OSPF. And if you guys want, and we have extra time, I'll use the same overlay and we can do a BGP, an iBGP, and an eBGP demo if we run out of time, if we have time. So, and if not, I'll make it a boot camp if you guys like. So config T, let's change the host name on this to router 3, R3. Let's make sure we can telnet, line VTY, 0 space 4, no login, password Cisco, transport input all. Here's where you can say SSH, telnet, etc. I'm on my computer. It's simpler this way. Now what we're going to go to interface, loop back 0, IP address. We're going to do 3.3.3.3. We're going to do 255.255.255.255 because it's a /32. We'll do a no shutdown even though it already went up. Now router 3 is connected to router 1 on G0/0. So let's go to interface. Let's get out of this interface. So interface, so you can see it, G0/0. Now we're going to enable that interface, but there's no IP address, so nothing's going to work. Now that interface is going to connecting to the far end. Oh God, this is ugly. Is going to connect to the far end of here. So what we need to be is on the same subnet of router 1's G0/1. So if this is .5 and the subnet begins at .4 and ends at .7, 172.160.0.4, that's what the router sees. Then we can do 172.16.0.5. We can do 172.16.0.6, and then 172.16.0.7 as the broadcast. So we can't use that. So now let's go to this router 3, and let's have a party with it. So router 3, we're going to go to interface. Interface, G0/0. And we're going to do an IP address. We're going to do 172.16.0. What? What's that far end of that G01 on the other side? .5, so it's got to be a .6, right? .6, 255.255.255.252. Okay, now we got to cover this link on router 3. This link goes from here to here. So what would those subnets be? Okay, so interface G0/1. Okay, now we're interface G0/1 while we're having some fun. Let's go over to here. Now that one's going to router 2, right? Let's be very, so router 2, it's G0/1 on router 2. So let's look at router 2 at our G0/1 to make sure we're in the right subnet. So it's going to be 9. So if it begins with an 8, we can use 9 and 10, and then 11 is the broadcast. So that's going to have to be .9. So interface 0/1, IP address 172.16.0.10, 255.255.255.252. No shutdown. Now let's enable OSPF router. OSPF 1 network 3.3.3.3 0.0.0.0 area 0 network 172.2.16.0.0. Let's do which 0. Actually, let me go just check and make sure I know which subnets are on over here. But you got to be in configuration mode to do that. .172.16.0.4 0.0.0.3, area 0. The .8 subnet. So if we did this right, every router should have everybody else's routes all in area 0. So let's see. Router 1 should be able to reach router 2 and router 3. Can we? We can see the loopback address of router 3. We can see the loopback address of router 2. Can we reach them? Show IP OSPF neighbor. Now look at that. We've got 2 neighbors there. We should have 2 neighbors on every one of these. Show IP OSPF neighbor. We've got 2 there, which is what we should have. And if we go over here, it's my recommendation. Show IP OSPF neighbor. Okay, you can see everybody's connecting to everybody. Now, when you can see this, note, I'm working pretty hard here to verify connectivity. Can I ping across the link? Do I have routes? Why? See, if I don't have this fundamentals down, everything else we're going to do is just going to break. So I like to start by verifying that everything works before I lay things. So if I was going to build a building, I'd hire a construction crew to lay the foundation. I'd hire somebody to test the foundation. Then they'd start building. Then I hired an inspector to check at each stage. That's the way I check my work, the same way. So now let's go back into this environment. Now, what do we really have here? We have 3 routers, and every one of these routers is in area 0. This is our backbone. Now let's take this and let's create a new area. Okay, so how are we going to do this? On this particular router, we'll pick a new subnet. Anybody, and you know what, I don't remember which subnets we've used so far, so I'm going to just pick something in a totally different range. So we're going to do interface. We're going to do G0/2. No, and then we're going to put an IP address on it. We'll do IP, ADDR, 192.168.1.1, 255.255.255.252. Do a no shutdown on this interface. We'll go back to OSPF. We'll go to router, OSPF 1. Now let's add this network, 192.168.1.0, 0.0.0.3. Now let's put it in another area, area 0. Now we'll go to router 4. Over here. Oops. We better config T. We never turned the interface on. Interface. Oh, yeah, we did. Okay, good. So let's just go to our router 4. We may have to configure router 4 from scratch, which is okay. We know how to do this. We've been doing it all week for 2 weeks. It's been fun. So let's come back and see what's going on. Okay. Yeah, that's the good news. Everything's still working. Okay, so now we're on this new router. Good news. Everything's still working. That's really weird. Okay, so now we're on this new router. We'll give it a name. Call it router 4. Easy. VTY 0 space 4. The loop back on it. Now we'll put an IP address in the Ethernet port. We're going to pop in area 0, and then over here we'll put the IP ADDR 192.168.1.2, which should be the other end of the link. Just wait and see what happens. If we did this right, we should see the line come up. They can see it. Line protocol comes up. If we did it right, if we got everything in OSPF, we should see a neighbor adjacency change. And we haven't seen it yet. So did we forget to put OSPF on an interface? Is one of the interfaces not turned on? Got to check. So let's do a little debugging. Now we reached the 192.168.1.1 on route. Yeah, that's right. We ping the far end of this link, 192.168.1. Ping 192.168.1.2. We reach it? Oh, we can. Okay. Okay, that's up and running. Show IP OSPF neighbors. We only have 2. So what's going on here? Why aren't we running OSPF? Show IP int brief. The link is up. Now let's look at our running config. Did we configure OSPF correctly? Oops, let's go back and see what we did over here. So we've got 4.4.4.4, which should be correct. And we've got the wrong subnet in OSPF. That's why it's not working. So what are the links we chose over here? 192.168.1.1. Okay, what is the interface that we configured on this router? 1.2. Is that in the same subnet as this? 192.168.0.0. So this command that I put in here will get us from 192.168.0.0, 0.1, 0.2, and 0.3. So no, this doesn't work. So we put it in here wrong. So what do you do when you do something wrong? Router OSPF1 config T router OSPF1. Now, when we get to router OSPF1, we're going to type in no for this. Control A gets us to the beginning of the line. Now we're going to remove that. Now what we're going to do is we're going to fix this and pop in the right subnet. And the right subnet is going to have a 1 in front of this. Now let's fix this. Let's see what happens. We should be getting a neighbor adjacency. Received a mismatch. Really, that's not good. Mismatch area. We got a problem. Something's not liking it. But, at least we can see what's going on. We received a mismatch ID. Why? Do we have a wrong loopback address? Do we have the wrong address? We've got something that's wrong here. So we have to debug. Let's look what we figured out, because this is obviously not going to give you what you're looking for. Oh. Anybody see the problem here? What area was this supposed to be in? Area 1. What area did we put it on here? Area 1. In fact, this is how good these routers are. Received invalid packet, mismatched area ID. Received invalid packet, mismatched area ID. So they literally tell you. Let's fix that. See how easy it is. Config T. And this is why you debug router OSPF1. But you got to be able to type router right. Put a no in front of this. Now, by comparison, let's go back. Let's get rid of the no. Get the area right, because remember, this is an area border router, or a router that goes to another area. Now let's swap that. Whoa, look at that. OSPF adjacency change, loading to full. So how many neighbors is this router going to have? Router 2, it should have 3. Show IP OSPF neighbor. Look at that. Now here's where it's going to get interesting. Let's get out of here. Let's keep this up and let's close this. If we go to router 1 over here, look at the routing table. Show IP route. Look at that. Why is this link intra-area? And why is this link intra-area? If router 1 is in area 0, and router 4's loopback is in area 1 and link is area 1, that's why it says intra-area. That's why it says intra-area. I hope that kind of makes sense to you. Let me just check something real quick. That's why we like it. So maybe we'll give you one more. Let's add one more router to this. Have some fun over here. Let's really get deep into this. So now let's add another link. While it's doing its thing, bear with me for a minute. Now we have this link. Now let's give this a new link. No, we don't want to do this. Let's see if I can remember how to do this. Okay, so now, look, when we looked at router 4, I just want you to see if we look at the routing table of router 4, show IP route. Note it's got a lot of routes, and every route that wasn't in its area is going to be intra-area. But you can see the routing table. So let's go have a little bit of fun on router 6. Enable. We'll configure this guy. We'll call it a host name. We'll call it R6. Let's do enable password. Cisco, because it's easy to remember. Interface loopback 0. IP ADDR 20.20.20.20. Okay, what subnets exist in the routing table? We've used the 172.16.0, .4, and .8. But what haven't we used? We haven't used the .12. So we're on router 6, so it's going to be G0/0. We can say int G0/0 IP ADDR 172.72.16.0. So the next subnet begins at 12. So we've got .13 and .14. So let's make this .14. Okay, so anybody that wants to know why we skip the initial configuration, the initial configuration is a series of questions like a wizard. Do this, do this, do this. Unfortunately, there's basically nothing that happens automatically, whether it's an AWS service or a Cisco service that actually works. So when you train network engineers, you tell them never to use the automatic. By the way, if you're working on the cloud, don't use any of their automatic anything either, because it's going to break stuff for you. So that's why we manually configure all network devices.
So the configuration that people are asking about skipping is it's like automated template type thing.
It's an automated template that will always yield an incorrect configuration.
Gotcha. So
most likely.
So it's not that you're skipping configuration, so to speak. You're skipping the automated.
Exactly.
Okay.
Everything we're doing here is we're configuring it. We're just not using the automated. We're actually doing it manually. Let's go to router 1, and we're going to do some experimental things with this so we can play around with it. When we configure this, you have to remember I'm a network architect, and though my CCNA number is 7417, it's Cisco. When I left engineering and became an architect, once you become an architect, you don't touch routers anymore. In fact, all architects don't touch the technology, we design it. So, I've been designing this stuff for so long, it's actually really fun to play with. So let's go to let's do the show IP int brief. Big T. Let's go to interface G0/2, and it's got to be on the same subnet as the one on the opposite side. Does anybody remember the name that I wrote on router 6? I know I sure don't, so let me do a show IP interface brief. And it's going to be .14, which means this is .12, which gives us .13, .14, and .15 is the broadcast. So this means this is going to be So this is going to be .13. So 172.16 .0.13 255.255.255.252. Back to the beginning of the line, because we can see I typed 172 incorrectly. That's how easy it is to do. I called it area 3 on this one. Yeah, let's make sure it's area 3. Okay, so let's do this. Let's wait, see if we see a neighbor change, a link come up on both sides. Whoa, we got a new OSPF neighbor. So let's make sure it's on both sides. Show IP, OSPF neighbor. We got all 3. Let's make sure we've got a neighbor over here. Okay, so now if we do a show IP route on this guy, notice how everything is intra-area? Because everything is learned via intra-area. Now let's go to router. I haven't done this in a while, so we're going to have to play with the configuration commands a little bit because it's been a long time. But let's go to G0. Let's go to router 1. What I did is I changed it to a totally stubby area. So it's going to form a new neighbor adjacency. I may have to put it on both sides. I forget. It's been a couple of years. I may have done something that's a little goofy. Show IP OSPF name. Done. So that didn't work out so well. Let's go to that. You may have to agree. If not, I will definitely show you this. I don't remember if to put it on one side or both sides. So on router 6 now, if we do a show IP route, now look what we see now that we're a totally stubby area. We see our route, and all we get is a default route. Now because of this router, let's look very carefully over here. Router 6 is a totally stubby area, which means if I do a show IP OSPF database, what kind of links do you think we're going to see here? We're going to see the router links, the network links, and just the default route that's coming in as a type 3. Now let's get rid of the stub area configuration. Let's see the difference. Show, run. Router, OSPF1. Excuse me. We'll make it a regular area. Now we should be a regular area, so show running config, make sure we deleted it. Ah, we still have area 3 stub in there. And now we got to go over here, do a show run, see if we removed it from this side. Haven't. Okay, we got rid of the stubby area. So now what's this database? What's this database going to look like? Show IP OSPF database. Remember, you saw one router. You had a now look at this database. It's a lot fuller. Now, why is it? Because now that we're a stub area, and I sent it to send no summary LSAs, we didn't have these before. We just had the default route. But now we've got more. We've got all the information from all the areas. That's why we do this. Now, heck, while we're at it, let's take router 4. Let's play with it a little more. Let's add another loopback. Config T interface int LO 10. I don't even remember int because I don't even know LO 10. IP ADR 64.64.64.64. Let's go back to router 1 now. What are we going to see in the routing table? Ooh. All of a sudden, we got this type 5 external LSA. 64.64.64. Note it says type 5. Why is it type 5? Because this router redistributed or translated Bulgarian to Greek and popped it into router 4. So now when we look on this routing table, look, it's going to look a lot different. Show IP route. And it shows as an OE2. OE2. So I kind of hope this is making sense what we're doing. We're walking through this. And as we walk through this, I can make it a stub area and we lose different types of LSAs. And that's really what's going on is the LSAs determine the kind of things that we're doing. So what are the kind of stuff that you're really looking for? We showed you how to look at the database. We showed you how to look at neighbors, showed you how to look at the routing table. Now, what if we wanted to configure the router ID? We could basically tell it, if we did nothing, it's going to pick the loopback address. But so let's just out of curiosity show IP OSPF database. We can see this is our router ID from the loopback address. Now, if we had multiple loopback addresses and we wanted to be careful, what we could do is we can go to config T, we could go to router OSPF 1, and we could potentially tell it which router ID to use. Do that. 1.1.1.1. Do you think the router ID is going to be now? The same 1.1.1.1 that it was before. Note that the database is going to look a little bit different where you're at. In area 0, every router will have an identical database of everything outside of the areas. So now let's think about, we could play with this. And now you know what a stub is, and not so stubby areas. A stub no summary is. etc., etc., etc. So let's talk about another thing. What if, for example, we wanted to add a switch? We're bringing a switch. I did bring in a switch, right? No, I meant to add a switch. Guess I didn't. So implement, add an object, add a node. Let's bring in a switch. Let's make ourselves a nice happy switch. Now we're connecting a port to the switch. The only reason I'm doing it is I want the port to come up. Ugh. Now let's turn the switch on. Let the switch come up, get on the console port, we'll watch it boot. They take a little while. Servers, Xeon workstations with a 0.5 terabyte of RAM, they're just, they run these big power on self checks. They're real slow to boot. It's not like a hobbyist computer that's optimized for video games that boots in like 3 seconds. Should be getting there, etc., etc. Switch is coming up, etc., etc. Life's good. Okay, enable. Config T. Let's give it a host name. Actually, let's just call it SW1. Now, let's pop an IP address on this port. It's going to be some ridiculous one. We're just going to make it up as we go along. Interface 0/1 E880R 192.168.10.1 255.255.255.0. We're going to make it a LAN segment. No shutdown. Router OSPF 1 network 192.168.10.0.0.0.255. Area, let's say 3. Let's call this a passive interface. Auto sync, G. Which interface was this that we just configured? G0/1, G0/1. Like 0/1. What we do is we would tell it the passive interface gigabit Ethernet. I don't remember which one it is. And what that will do is it'll tell an interface to participate in routing, but not form a neighbor adjacency. So let's go back to the switch a little bit more. The port should be shut down. So a show IP interface brief will show us the port shutdown. Gigabit Ethernet is up. Okay, so if that's really the case, when we get to router 6, we should have all of our interfaces up. And if we do, we put everything in our routing. If we go over to here to router to router 4, we should be able to see all these routes, including the new route that we just popped in there. Oh, look at that. We can. It's an intra-area route. So let's do this. Let's see if anybody has any questions. Let me figure out how to shut this. Hold on one second. Okay, Chris, does anybody have any questions?
Let me take a look.
I can no longer see the YouTube window, so.
Well, can you see the StreamYard window?
I sure can, so I'm completely dependent on whatever yours. Because we covered a lot of stuff today.
Here we go.
Eric Stoltz, I will say this. I said in the beginning, I've said it every single day. There is no reason to buy any content other than the Cisco Press book that we gave you and this. I would not buy a Udemy course. I would not do any of it. I would read the Cisco Press books that we told you, which are the official Cisco manufactured books. And I used to teach these kind of things to Cisco engineers when I worked at Cisco. So you're getting official Cisco training. So follow the Cisco training thing. No boson needed. Get the Cisco Press book by Vernon Odom. There's a volume 1 and 2. It covers about the 2,000 pages of material that we're covering throughout these 2 weeks. And they're what you should use. Always, always, always go to the manufacturer. That's what we do. Every documentation, everything we do always comes from the source. Always, always, always. Great question, Eric. Please go over the area types again. Are you talking about area types or are you talking about LSAs? So I want to make sure that I completely understand what you're doing. So Anthony, could you let me know if you're talking about area types or LSAs? And while we're trying to figure that out, Chris, if you want to bring in the next one.
The next one is about the book. They're asking for the title of the book. And Evdokia just put the link directly to the book in the chat box.
Okay, great. It's the official Cisco Press Vernon Odom book, and Evdokia put a link to the book.
It is literally called Official Cert Guide.
Right, and it says Cisco Press on it. It's got Vernon Odom's book on it.
This is what it looks like.
There's a volume 1 and volume 2. It's part of a package. You can usually get the whole package for $30, $40. It includes practice test, practice lab. It's literally everything. Yep. That book is worth $500, and they charge $30 for it. It's for the 2. It's fantastic. I've literally taught at least 10 people straight out of that book and nothing other than that book, and then they pass the exam right afterwards.
Yeah. So I wanted to make it clear because it can be kind of confusing when we say get the official cert guide. That's the name of it, official cert guide.
And I like Boson. They're a good company, but on a scale of 1 to 10, Boson's a 5. And the Cisco Press book is a 10 because Cisco made the book and Cisco made the exam. And Vernon Odom is a Cisco guy like me. His CCNA number is like 1060, so he's old school Cisco. That's what we're referring to.
This is what it should come like if you get the official guide. It should come like that. Obviously, I have volume 1 somewhere else right now,
but that's the point. You've got our own employees. My CCI number is 7417. You better believe I've got a copy of that because I work off of official materials for everything I do. And Chris has got a copy, and I bet you Leo's got his own copy in Brazil as well. I don't know, half of my team all over the world has the Cisco books. Okay, so I can do that. Chris, how many more questions do we have? Because this is a CCIE level question, which I'm happy to answer. It's not part of the CCNA program. I just want to make sure we have time to answer everybody else's question.
Yep. The only other question right now is this one.
What lab goes with the official book? The official book has its own official labs that are attached inside the official book. Do everything with the official books, and you don't need anything else. We've given you the course, and we base our training off of the official materials. And follow that plus the official book, and you are good to go. So with regards to areas, we have a normal area which receives everything. Type 1 LSAs, Type 2 LSAs, which are the local ones. Type 3, which are those intra-area LSAs. Type 5 LSAs, which are external LSAs. And Type 4 LSAs tell us how to reach the router that has the external LSA. So that's normal. Now we can create something called a stub area. And what is a stub area? A stub area basically says, you have access to the Type 1 and you have access to everything in your area, but you either get, but you don't get all the things. So for example, in a stub area, and let's say a stub area is area 1, you'll know of all area 1's routers and network links, and you'll know about how to get to area 0. And once you get to area 0, all those routers are there. So if you've got a not so stubby area, that's basically that same thing, but it's enabling you to take external routing information from RIP, from BGP, from Eigrp, from intermediate systems to intermediate systems, and import that data that makes it an external route. So not so stubby, you're allowed to have it. Totally stubby means you only have network and router links and a default route. So stub means you've got a partial of your things. Not so stubby means you've basically got your own, and you can take an external links from an external routing protocol. When you redistribute that into OSPF on your router, it's considered a Type 7 LSA, and that router translates it to a Type 5 LSA, which is what's seen by the rest of the router. So that's called a not so stubby area. And a total stubby area is basically a stub with no summary routes, which basically means just the default route, and that's it. So it's whether you get stub and summary routes and no externals, whether you get, and that's a stub area, whether you get a totally stubby area, which basically has your own intra-area routes and a default route to area 0. And we have a not so stubby area that enables us to, what's the word I'm looking for? Take external routes and redistribute them into OSPF. That's a not so stubby area. And that's a great question. And it's definitely a CCNP, CCIE question, but it's definitely a good question. I just wanted to make sure we had the chance to do that.
So, Mike, I wanted to follow up about this official book because a lot of people keep asking about resources. So I'm reading straight off the content here for everybody. This, when you buy the official one, not used. If you buy it used, there's like a 50-50 shot you get all this stuff. But if you buy this from Cisco, you get access to the companion website, which contains more than 600 unique practice exam questions, CCNA network simulator software, online practice exercises, and more than 2 hours of video training, in addition to the actual book. So along with that simulator comes with labs that they have prepared for your development. So that's the reason we recommend going to this official, et cetera, is because for $50, you get stuff prepared by the people that are making the exam. And
Exactly.
it's not just the book. It's the reason we recommend it is because it comes with all of that access through their website.
And it's not like somebody that just made it up in their basement, someone that's just trying to teach on their own. This is one of Cisco's best, one of their original CCIEs that's working for Cisco, writing for Cisco, for training you for Cisco. Now, I like Boson, but you compare that. It's like if you want a Ferrari part, do you get it from Ferrari, or do you go to Fred's Aunt Martha that knows how to make something in the backyard by using a drill and some sandpaper and things like that? It's nowhere in the same league. Yeah. Always go to the source when you can. We do. I'm from Cisco.
And we continuously point out that Mike's CCIE number is 7617.
7417.
7417. So Wendell Odom's CCIE number, and I'll let you explain where these began in just a second, Mike. Wendell's CCIE number is 1624.
I really want you to figure this out. So in Cisco terms, we're a little geeky. We started counting at two. The first CCIE was 1028. Why? Because we thought 2 to the 10th would be cool over at Cisco. So by the time I took mine in my number 7417, 3 million plus people had attempted Cisco certification, and I was the 6400 guy to pass. Now that was when the exam was 2 days, like when Wendell and I took it. The first day they made you build something that was impossible. The next day they basically sent 90% of the people home because they had failed. The people that survived, which was like 1 out of the 15, would get, or 2 would get to configure their things before lunch, and then you'd go to lunch. And here's what would happen. When you come back for lunch, you were either sent home because you failed, or if you were there, you'd come back to a completely broken network. They'd recable your network, they'd change your subnets, they'd change your routing protocols, they'd mess up your redistributions, and they'd cause you all kinds of loops. And then they'd say, here, you got a couple hours to fix it.
Yeah.
That exam had like a 90-some% failing rate. You can see instantly when they took the CCI exam, from a 2-day exam to a 1-day exam, the pass rate went up by about 80%. And it became a much simpler exam. That's why the CCI today is still very appreciated, but it's not like it was for the guys that had CCI numbers less than 10,000. His number is 1100. What that means is there were no books for him to read.
Right.
He had to read all the RFCs, all the Cisco documentation like we all did, and there was no training. He had to know it in such depth to pass it. So when you get one of those guys that's teaching, listen, he is awesome.
Yep. And so not just Wendell, the technical reviewer for all of this content is 1837. And contributing authors are 4594 and so on and so on. So
yeah,
this is all created by people that didn't have this type of stuff to prepare. And so they created this for you to prepare.
Exactly. So the reason I make so much content out there is because when I wasn't available, there was none. And when I look at what's out there, none of it impresses me. So it's like, okay, I'm going to give you Cisco materials because I want you all to be successful.
Yep.
So, that's kind of the reasons we're kind of talking about this. Now, I think I'm going to end today. Chris, can we go 15 minutes more for me to talk about network types so we can talk about something new tomorrow?
If by 15 minutes you mean
15
minutes? Yes.
Okay, so let's just talk about the concept of a network type with regards to OSPF. And realistically speaking, there's just 2 kinds of networks. There's a point-to-point network, which is basically a WAN link. And we've got this kind of broadcast multicast access. So I know I've demonstrated this very heavily, but let's just go through this for about 1 more minute. Couple minutes. When we've got routers on our LAN link, this is what's called a broadcast multi-access thing, and that's why we've got that election of this designated router, or this is the designated router on the LAN, this is the backup designated router, and everything else that's not a designated router or a backup designated router is called a DR other when you do the show IP OSPF neighbor. And you can see that if we go to our labs. I just want to walk you through this. I just want everybody getting a great experience. So when we go over here, if we go to router 4, for example, enable Cisco show IP OSPF neighbors, you can see the neighbor is the backup designator route. But that's all I really wanted you to see, is that you could see that was going on with that. So going back to the interface, the interface knows. It automatically knows if it's broadcast or non-broadcast. And let's see how I can show you this. Well, maybe not. I'm just going to show you in a slide because I don't even know where this window disappeared to. Oops. Nope, not this window. Bear with me, guys. Okay, so Note when we look, when we go over here, if we're looking at the show IP OSPF interface, you see where it says the interface is up and the IP address. It will tell you the network type over here. So you can see that directly in the OSPF command. I'm just trying to see if there's anything else that we missed that I really wanted to cover. Yeah, I wanted to show you this. So if it's a point-to-point interface that you had, like a serial link or a different type, if we were to set it as point-to-point, like over here, we're going to tell OSPF not to have the election to make it look like a WAN link. It's going to say network type point-to-point, but we're not going to do that on a WAN link, on an Ethernet link ever. Realistically speaking, it's going to be very rare. There's going to be specific use cases to do it, but point-to-point links, like a cable, like a serial link, they show up as point-to-point. Ethernet, why is Ethernet? Well, Ethernet goes into the switch, right? What does the switch do? Broadcast all ports except for the one it came in on, at least for unknown frames. And so that's why it's a broadcast multi-access for Ethernet ports. Same kind of concept. And we can see, we can go walk through our show IP OSPF neighbors. We'll see that they were full, I showed you. And if we look at the interfaces that are running OSPF, we can see the type of interface and the number of neighbors. How many neighbors can you have on a point-to-point link? One. Let's so talk about things that have to happen for it to work. Your interface on both sides need to be on the same subnet. We can't have any ACLs blocking out OSPF hellos, for example. The hello and dead timers must match. Can't have one router claiming to be 1.1.1.1 and another router claiming to be 1.1. What's that mean? The router IDs have to be unique. Two routers with their links have to be in the same area. Note, we got the area wrong and poof, it didn't work. And those are kind of your main things that you need to remember between OSPF neighbors. Here's a good one. If you're ever trying to troubleshoot something and it's not working, and you do a show IP OSPF interface on both routers, let's look very carefully at what's going on here. On router 1, show IP OSPF interface. Timer interviews configured. Hello 10, dead 40. What's that mean? Every 10 seconds, Eva Doikia, hello. And every 10 seconds she says, hi Mike. Every 10 seconds, Cindy sends Eva Doikia a per message or a hello message. And every 10 seconds, Eva Doikia replies. If Cindy sends 4 hellos and Eva Doikia doesn't reply for 4, the link is marked as dead. And then Cindy and Eva Doikia aren't talking anymore, which is really sad. They assume the link is dead. And then Cindy reaches out to her good buddy, Eva Doikia, over there in Hungary. And she finds a backup path because this path went down. She finds a new path. And that way she gets to talk to her friend. And Cindy places lots of international phone calls and does all kinds of cute things. You have absolutely no idea the kind of ruckus my cat Cindy could do. And realistically speaking, if we ever wanted to shut down OSPF for any reason, there's the ability under OSPF to enter the shutdown command to shut it down. So, and once we shut it down, what's it going to look like? Show IP OSPF neighbor. Wait, we got to, well, you know, shutting. This will happen if it's for some other reason. So let's get that out of there. But that's really what I wanted to walk you through today. I really wanted to walk you through OSPF, areas, how they work. So what did we do today? We talked a little about the ping command and how to use it to see if the network's good. We talked about traceroute and tracing your way through the network. We talked about OSPF. We talked about link state routing protocols and the way they work. We dealt with the type 1 LSAs, which are router LSAs. We talked about type 2 LSAs, which are network LSAs. Again, this is way above the Cisco Certified Network Associate, more of the CCNP thing, but that's okay. We talked about stub areas, totally stubby areas, not so stubby areas, mostly CCIE level stuff, but that's okay. We talked about the hello messages, the dead timers, and how OSPF calculates a path, etc., etc. So we pretty much covered most of OSPF today. So I guess I'm going to end it with this. Do you have any more questions? If you do, let's answer them. And if not, I'm going to ask you to type one or two last commands, and we'll get ready for party time tomorrow, which is going to be really, really fun. Are there any other questions for me there, Chris?
So we have people asking if they can see Cindy.
Yes.
And then, hold on. We got some actual questions first, but I was giving you the heads up there.
Okay. Ferdy, I think it's depending upon the person. I thought the CCNA was exceptionally easy. I passed it in 4 days. I have seen other people that knew literally zero about networking pass it. So I don't think it's very hard. The key is, do you know subnetting? Do you know basic switching? Do you know what an IP address is? Do you know what subnetting is? Do you know the OSI model and the Internet Protocol model? And if you do, it's a relatively simple exam. Now, I will tell you this, Ferdy, the Cisco exams are what I call straightforward exams. And what I mean by that is you could take an Amazon exam, and the hardest part of an Amazon exam is reading through the question, because they stick the word elastic in 50 different places, and you read through these exams and you're like, what are they even asking? And once you read the question the third time and figure out what they're asking, it's a simple answer. Not so with Cisco. Cisco gives you very strict, clear questions. And it is very obvious if you know the material they answer. So Cisco materials are very clean. Cisco writes in a certain way to make the questions very understandable. So I found the CCNA exam to be extremely easy. I will tell you, Ferdy, I've coached now, I can't tell you how many people. I've never had anybody fail a CCNA exam. Now, quite frankly, the only CCNP exam I've ever seen anybody fail was the troubleshooting exam. That was one of the people that I trained. And this was a person that basically took the troubleshooting exam like this, back when they used to have the CCNP exam. He said, Mike, here's the thing. I have more money than time. And I said, yeah, so. And he says, I'm not ready, but I'm going to go take this troubleshooting exam and see if I can pass it. And I said, but you said you're not ready. And they said, yeah, but I could study, or I could just pay the couple $100 and pass the exam. And if not, I'll just pay a couple $100 and take it again. And I said, that's not the way I recommend studying. And he says, Mike, you recommend that I learn the job, not the certification. I said, you're right. And he said, so I'm going to get through this certification the laziest, fastest way I can. And I said, okay. I will tell you, this person went on to become such a good network engineer that they made it to the top of, of one of the world's best networking companies. And he rose like a rocket ship. The key is he focused on all the things. But I don't think it's going to be hard for you, Ferdy. I think it's going to be a very simple exam. I think if you don't know networking, it's a very challenging exam. I don't really let anybody tell me things are hard, Ferdy. No, I have a different perspective. I was told I would never walk again, and I literally spent 6 hours a day in a physical therapy center every single day for almost 8 years straight. And I still spend 3 hours a day in a physical therapy center just to be able to walk down the stairs of my house every single day. So to me, that's what hard is. I don't think you'll have a hard time with this, Ferdy. I think it'll be easy for you. I think you've gotten some solid training this week. I think you'll be good. Sadie, still confused what is broadcast versus multicast? Okay, great question. Every one of you, listen to me. You have to listen to me no matter what. I am broadcast. That's what a broadcast is. By comparison, now, Sadie, 50 of you are going to subscribe to pictures of my cat Cindy. And only of the 50 of you that subscribe to my cat Cindy can see it. I send the cat Cindy. Eva Doikya sees it. Abigail sees it. Chris sees it. Mesh sees it. But only the people that subscribed. That's a multicast. You want it, you got it. You want it, you got it. You want it, you got it. A broadcast is, everybody listen to me right now. That's a broadcast. The multicast is, all of you that want it, you got it. Your food's delivered. Like that. Great question, Sadie. Great question. Hope I made that in not too obnoxious manner, but I don't want you ever forgetting it. What are we covering tomorrow? I'm not sure what we're covering tomorrow yet. My team is going to be sending me the slides tonight and the topics from the official team, and we're going to have a party with it. I can tell you that. I'm going to bring Cindy in about 2 minutes. Even like your per messages, love them. I'm going to bring her. She's this. Are we ready to see Cindy?
Yes, we are.
Let's make sure she's in because she did go out this morning and she was terrorizing some people. So let me go see if she's in her bedroom. And if she is, I'm going to bring her. I did hear her. Could you come with me, Princess, for a minute? Just for... So we can all see Cindy. So everybody can see my beautiful, beautiful helper in the office. This is my Cindy. She's very sweet. She doesn't like to be held, but she does like to sit on us. Okay, you can do whatever you want, Cindy. Not right now. Okay, well, that's my baby Cindy. She comes when she wants. She goes when she doesn't want to be held, but she's a lovable, sweet, wonderful little child. Now, we all know why I always have fur on me all the time, but wouldn't trade my Cindy for anything.
And why you're always sneezing.
And why I'm always sneezing 24 hours a day, but I wouldn't trade my Cindy for anything. And the really funny thing is, I was always a parrot person. I had parrots. I love birds. My wife likes cats. I go to the cat rescue. The little kitten puts its paw up to the glass. I put my paw up to the glass. I'm not very mechanical, so the cage was locked. So it was like a glass window thing. It took me like 5 minutes to figure out how to open the door when it was just a lever. I go in there. The cat rubs against my feet. I have a foot problem. I literally sit down on the chair. The kitten jumps up in my lap, purrs, and falls asleep. An hour and a half later, she's still in my lap. And guess what? That little mini lioness, Angelo, thank you so much. She wasn't going anywhere. Thank you so much, MJ. Yeah, she doesn't love to be held, but she loves to come over on her own terms. I'm a dog person, but I love cats too. I love all animals with fur or feathers. I never was a cat person, but this one, oh my God, she's just my little baby girl. Thank you so much, Sharon. Ivadikya, I know she's always looking for you. She actually asked for you by name. So if you're all here and you had good time, type hashtag CCNA. That way I know we all had a great time. And of course, tomorrow we will get involved in some fun networking. I'm excited to find out what we'll even be talking about. We do follow the Cisco curriculum. So if you've got the official curriculum, you're going to know where we're headed next. Your brother gave you the CCENT, CCNA. I'd probably change by the new one. So here's the thing. There used to be a CCNA divided into two pieces. You could do a CCNP. This is a single exam, so it's a little different. They're going to be 90% the same, but for the cost of the book, which is less than $50, I think you're better off just getting the newest version. Yeah, Alex, we're going to leave the IPv6 off of this curriculum. There's a tiny section in there, but we're going to focus more on the heavier duty stuff that's more related to getting cloud hired or network architect hired, which for the most part is IPv4 stuff. That's where my strength lies. Yeah, 1624. It's pretty incredible. Sharon, I'm honored and privileged to try and go out there and help you. Mufaz, it's always good seeing you. Okay. Well, everyone have a wonderful, wonderful, wonderful night. We'll get back to it tomorrow. We'll continue through the week. By the end of this week, you guys should all have some serious network knowledge. And go out yourselves and get yourselves network administrator jobs, network engineer jobs, cloud architect jobs, cloud engineer jobs, or whatever it is that's going to make you happy. That's the whole point. Get cloud hired, network hired. Actually, you know what? On ending, can you all type a hashtag cloud hired, and then we can end for the day. Have a wonderful day. It's an honor and a privilege to be with you. And look forward to seeing you tomorrow. Hashtag cloud hired, please. Take care, everyone.